Hello there, and welcome to Life Beyond Seen, where curiosity settles in quietly and science takes its time unfolding. Tonight, we turn our attention to something the ocean does only rarely, and yet when it does, even the largest ships ever built can find themselves suddenly shockingly small. The phenomenon is known among sailors as the Three Sisters. It sounds almost gentle, almost like a children's tale. 3 waves, arriving one after the other. But in certain conditions, those 3 waves rise higher than logic suggests they should, higher than forecasts predict, higher than steel designers prefer. If you have ever stood on a shoreline and watched the sea for a while, you may have noticed something curious. Most waves roll in with a rhythm, a crest, then a trough, then another crest, predictable, reassuring. You begin to feel that you understand the pattern, but every so often the rhythm stumbles. A larger wave arrives, then another, and sometimes a third, even bigger still, stacking energy in a way that feels almost intentional. The sea gathers itself, and for a brief moment it becomes something else. Where are you listening from tonight? Are you near water, perhaps in a coastal city where the air carries a hint of salt? Or are you far inland, where the ocean exists mostly in memory or imagination? And what is the weather like where you are? Calm, windy, still. It is interesting how something as distant as an open ocean storm can shape events thousands of miles away, sometimes in ways we do not expect. If you find this exploration steady and absorbing, a quiet place to rest your thoughts while we examine something vast and powerful, I would appreciate it if you considered liking the video or subscribing. It helps this small harbour of long-form curiosity remain afloat and reach others who might enjoy a slower journey through complicated ideas. Now let us ease into the story itself. The term Three Sisters is not a formal scientific classification in the way that hurricane or tsunami is. It is a sailor's phrase, a practical phrase. It describes a sequence of 3 unusually large waves that strike in close succession. The first wave hits. Before a vessel has fully recovered, the second follows, and then the third arrives, sometimes the largest of all. The danger is not simply their size, but their timing. Recovery requires time, stability requires time, and in these moments time is scarce. To understand why this matters, we should first consider what a wave really is. It is tempting to imagine a wave as a moving wall of water travelling across the ocean. But in reality, the water itself mostly stays in place. What moves is energy. Wind transfers energy to the surface of the sea. That energy organises into oscillations. The water particles move in circular orbits, rising and falling as the wave passes, but largely returning to where they began. Under ordinary conditions, waves are distributed across a spectrum of sizes and periods. Some are small, some larger. They interact, pass through one another, and interfere. Sometimes they cancel each other slightly. Sometimes they add together. This addition is called constructive interference. When 2 wave crests align, their heights combine. If a 1-metre wave meets another 1-metre wave in perfect alignment, for a moment, the result can be a 2-metre crest. Usually this alignment is brief and modest. The ocean surface is chaotic, and perfect synchronization is rare. But in storm conditions, the sea becomes more organised. Strong winds blowing steadily across long distances, what oceanographers call fetch, create wave systems with similar wavelengths and directions. When many waves share similar properties, the odds of significant constructive interference increase. Now imagine not just 2 waves aligning, but several. The ocean does not think, of course. It does not plan, but physics does not require intention. If enough energy is present, and if conditions line up just right, a cluster of waves can reinforce one another in sequence. The first large crest rises higher than expected. The second follows before the energy is dispersed. The third arrives, adding further momentum. To a ship caught in that sequence, It does not feel like random mathematics. It feels like an assault. Modern oceanography has documented related phenomena under the term rogue waves. Rogue waves are single, unexpectedly large waves that appear in open water, often in otherwise moderate seas. They were once dismissed as maritime folklore. Captains spoke of walls of water 30 metres high. Scientists were sceptical. Instruments rarely recorded such extremes. That changed in 1995 when a platform in the North Sea recorded a wave approximately 25.6 metres high. It was named the Torsional wave, after the platform itself. The measurement was precise. The instruments were reliable. The data forced a reconsideration of what the ocean could produce. The three sisters are not identical to rogue waves, but they are closely related. Both arise from nonlinear interactions in wave fields. Both challenge assumptions about maximum expected wave heights, and both demonstrate that averages can be misleading. A storm forecast might predict significant wave heights of 10 metres, but significant in this context means the average of the highest third of waves. It does not mean that no individual wave will exceed that value by a large margin. Ships are designed with these statistical expectations in mind. Naval architects use models based on historical data. Hulls are reinforced. Stability calculations account for rolling, pitching and heaving. Yet even the strongest design must rely on probabilities. Absolute safety against every conceivable wave is impossible. The ocean's energy budget during a major storm is enormous. Wind speeds exceeding hurricane force can inject vast quantities of momentum into the sea surface. Currents interacting with waves can steepen them further. When waves travel against a strong current, their wavelengths shorten and their heights increase. Energy is compressed. Consider a large cargo vessel crossing the North Atlantic in winter. It may be over 300 metres long, constructed of steel plates many centimetres thick, reinforced by internal frames. It may weigh hundreds of thousands of tons when fully loaded. From the deck, the sea can appear vast but manageable. The vessel rises and falls in long swells. Crew members grow accustomed to the rhythm, then conditions shift. Wind direction changes slightly. A secondary storm system overlaps the primary wave field. Reflected waves from a distant coastline intersect with incoming swells. Beneath the surface, a current flows in the opposite direction of the dominant waves. None of these factors alone guarantees disaster. Together they increase the complexity of the wave field. When the first of the three sisters strikes, it may cause severe pitching. The bow climbs sharply, then slams down into the trough. Water can sweep across the deck. Containers, if not perfectly secured, may shift. The crew braces. The ship recovers, engines straining to maintain heading. Before the vessel has fully regained stability, the second wave arrives. It may hit at a slightly different angle, introducing roll in addition to pitch. The combined motion can stress the hull. Modern ships are flexible to a degree. They bend along their length in heavy seas, a motion known as hogging and sagging. When a crest supports the bow and stern, while the midsection is unsupported, the ship hogs upward. When the midsection is supported and the ends hang over troughs, it sags. These stresses are anticipated in design, but extreme repetition in short intervals can approach structural limits. The third wave in the sequence can be decisive. If it arrives at a moment when the vessel is already heeled over, its force can push beyond the angle of recovery. Stability curves, those careful diagrams in naval architecture textbooks, show a range of safe heel angles. Beyond a certain point, righting moments decrease. If cargo shifts or water accumulates on deck, that critical angle shrinks. Capsizing does not always require a single towering wave. It can result from cumulative stress and timing. Historical records contain accounts consistent with such sequences. In 1978, the German cargo ship MS München disappeared in the North Atlantic. Debris later recovered suggested structural failure from extreme wave impact. Although definitive proof of a Three Sisters sequence is impossible, investigators considered the possibility of multiple large waves striking in rapid succession. Fishing vessels are particularly vulnerable. Smaller than cargo ships, often operating in severe weather, they can be overtaken by steep breaking seas. Survivors of maritime disasters sometimes describe 3 massive waves, one after another, the last sweeping the deck clean. It is important to avoid dramatizing beyond evidence. The ocean is dangerous enough without embellishment, but the mathematics supports the plausibility. Wave height distributions in nonlinear sea states exhibit heavy tails. That means extreme values occur more frequently than simple Gaussian models predict. In practical terms, rare does not mean impossible. It means infrequent but inevitable over long enough timescales. Modern monitoring has improved dramatically. Satellites equipped with radar altimeters scan the ocean surface, measuring wave heights across vast regions. Buoy networks transmit real-time data. Computer models incorporate wind fields, currents, and bathymetry. Yet prediction remains probabilistic. The exact timing and location of a constructive interference event involving multiple large waves is not something we can forecast with precision days in advance. The Three Sisters phenomenon also depends on human perception. Sailors give names to patterns that stand out. 3 large waves in sequence are memorable. They fit into narrative structures. 1 wave is frightening, 2 is worse. 3 suggests pattern and intent. But beneath the naming lies physics. Nonlinear wave interactions can create wave groups. Within those groups, energy concentrates temporarily. A ship encountering the peak of such a group experiences what feels like targeted aggression. Laboratory experiments in wave tanks have reproduced aspects of this behaviour. By generating wave trains of slightly different frequencies and allowing them to interact, researchers observe envelope modulation. This is sometimes called the Benjamin Fair instability. A uniform wave train can become unstable and break into groups with higher peaks. In controlled settings, engineers can watch a modest wave field evolve into clusters with crests significantly exceeding the average height. Scaling from a laboratory tank to the open ocean involves complexity, but the underlying mathematics is similar. Nonlinear Schrödinger equations describe the evolution of wave packets. Solutions predict the formation of breathers, localize spikes in amplitude. In physical terms, that spike can be a rogue wave. In temporal sequence, it can contribute to a Three Sisters pattern. We often imagine giant ships as invulnerable. Their size suggests dominance, yet scale works both ways. A 300-metre vessel is enormous relative to a human, but modest relative to a 200-metre wavelength swell carrying the kinetic energy of a storm system spanning thousands of kilometres. The ocean does not need to be consistently monstrous to be dangerous. It only needs a few moments of alignment. There is something humbling in that realization. Engineers calculate safety margins, captains monitor forecasts, satellites track storms, and still the sea retains variability that resists full control. The Three Sisters are not a supernatural curse. They are a reminder that complex systems produce extremes. In calmer seas, the ocean surface can appear almost orderly. Gentle swells roll under a clear sky. But the same physics governs both tranquility and violence. Wind transfers energy. Gravity restores balance. Interference shapes patterns. The difference lies in scale and alignment. As we continue, it helps to step back and examine how sailors historically interpreted such events before equations and satellites entered the picture. Long before nonlinear wave theory, mariners told stories. They described walls of water rising without warning. They spoke of sets of 3 waves. In those narratives, fear and observation intertwine, and understanding how those stories formed gives context to how modern science eventually caught up with what experience had already suggested. Long before radar, before satellite altimeters scanned the surface of the ocean from orbit, and before equations described the instability of wave packets, sailors told stories. Not dramatic legends meant to entertain taverns, but careful accounts passed between captains, deckhands, and fishermen who depended on accuracy to stay alive. Among those accounts, a recurring pattern appeared: 3 waves, not one towering crest out of nowhere, but 3 unusually large waves arriving in close succession. The first struck hard, the second harder, the third sometimes the worst of all. The phrase 3 sisters did not originate in a laboratory. It came from decks slick with salt water and from logbooks written in cramped handwriting under lantern light. It was a descriptive term. Sailors noticed that during certain storms, waves seemed to come in groups. Within those groups, 3 stood out. The name was simple, practical, and memorable. It was easier to shout 3 sisters than to explain the mathematics of nonlinear wave interference. If you imagine standing on the deck of a wooden sailing ship in the North Atlantic 2 centuries ago, the scale of vulnerability becomes clearer. The hull is timber, the sails are canvas, the only instruments are a compass, a sextant, and perhaps a barometer if the ship is well equipped. When a storm builds, the crew shortens sail and turns the bow into the wind. They watch the horizon constantly. They do not think in terms of wave spectra or significant wave height. They think in terms of survival. Accounts from the age of sail often describe sets of heavy seas. A captain might write that the ship encountered a most violent succession of 3 seas, each greater than the last. Another might note that after weathering one immense wave, the vessel was struck twice more before the crew could regain footing. These were not poetic exaggerations, they were attempts to document what had happened. In the 19th century, maritime insurance records occasionally mentioned sequences of large waves as contributing factors in structural damage. Wooden hulls could be stove in by heavy seas. Masts snapped not only from wind but from sudden changes in pitch and roll. When 3 major waves arrived back to back, the cumulative stress could exceed what a ship could tolerate. Fishermen in colder waters, particularly in the North Atlantic and the North Sea, were among the first to consistently describe the pattern in practical terms. Small vessels working in rough conditions were highly sensitive to wave timing. A single large wave could be ridden out by turning into it, but when the second arrived before the boat had fully recovered and the third followed immediately, recovery became uncertain. The North Sea, bounded by the coasts of Norway, Denmark, Germany, the Netherlands and the United Kingdom, has long been known for steep, short-period waves. The relatively shallow depth in many regions allows waves to grow taller and break more aggressively when driven by strong winds. In such conditions, sailors reported that large waves sometimes marched in 3s. It was not that only 3 waves were large, but that 3 in a cluster were noticeably more severe than the surrounding sea state. Early oceanography in the late 19th and early 20th centuries focused primarily on average conditions. Researchers measured wave heights using visual estimates and later mechanical devices. They categorized seas by Beaufort scale numbers and noted prevailing wind patterns. Extreme events were often dismissed as exaggerations. If a captain claimed to have encountered a wave far taller than expected, it was easier to attribute the report to stress, fear, or faulty perception. Yet the stories persisted. In 1861, the clipper ship Lightning reportedly encountered a sequence of enormous seas in the Southern Ocean that damaged its rigging and caused significant structural strain. While the exact details are difficult to verify, the narrative of multiple giant waves arriving in succession appears in several maritime chronicles of the era. Similar descriptions appear in whaling logs from the Pacific, where crews sometimes described 3 heavy combers striking within moments of each other. One might wonder why 3 became the recurring number. Why not 2 or 4? The answer may lie partly in human cognition. 3 is a pattern the mind recognizes easily. It suggests progression. 1 establishes the event. 2 confirms it is not random. 3 solidifies it as a sequence. But beyond perception, physics provides a basis for groupings. Wave trains generated by steady winds often exhibit modulation. Within a broader field of waves, clusters of higher amplitude form. Those clusters can contain several large crests in a row. Before scientific validation, however, sailors interpreted what they saw through the frameworks available to them. In some cultures, 3 waves were seen as a test of seamanship. The first wave challenged the ship. The second tested the crew's response. The third revealed whether preparation had been adequate. In others, the pattern was treated almost superstitiously, as if the sea were presenting a deliberate trial. Maritime folklore is filled with patterns of 3 knocks, 3 lights, 3 storms. It is tempting to dismiss these as narrative devices, but practical seafarers are not inclined to invent unnecessary drama. If multiple captains in different regions independently described similar sequences, there was likely an underlying physical phenomenon. By the early 20th century, steamships replaced most large sailing vessels. Steel hulls were stronger than wood, engines more reliable than sails. Confidence grew, ships became larger, crossing oceans with cargoes measured in thousands of tons. Yet reports of sudden, severe wave groups did not disappear. Instead, they took on new urgency. A steel ship might survive what would have destroyed a wooden one, but it was not invulnerable. In 1909, the British cargo ship Rarity vanished off the coast of South Africa. The exact cause remains unknown. Some contemporary speculation suggested heavy seas, possibly involving unusual wave groupings. Although definitive evidence is lacking, such disappearances reinforce the idea that the ocean could still produce events beyond standard expectations. As instrumentation improved, researchers began to notice that wave height distributions were not perfectly predictable. Early mechanical wave recorders, installed on piers and offshore platforms, occasionally captured sequences where several large waves arrived close together. However, the rarity of such events made systematic study difficult. In Norway and Scotland, fishing communities maintained oral traditions describing the 3 sisters in practical terms. Crews were advised that if the first heavy sea struck, they should brace for 2 more. Whether this was strictly predictive or simply a cautionary habit is difficult to determine, but the advice reflects pattern recognition. Experience had shown that extreme waves often did not arrive alone. The language used in these communities was straightforward. The 3 sisters were not described as mystical beings. They were a warning. Turn into the first wave, secure yourself immediately, expect 2 more. The simplicity of the guidance suggests that repeated observation had shaped behaviour. By mid-century, as oceanographic science expanded, researchers began to explore nonlinear wave theory more seriously. The development of spectral analysis allowed scientists to examine the distribution of wave energy across frequencies. They observed that energy could concentrate within certain bands, leading to the formation of wave groups. This scientific framework began to align with maritime experience. The idea that waves could travel in packets, with peaks and troughs of intensity, provided a mechanism for sequences of unusually large crests. The 3 sisters were no longer just anecdotal. They were consistent with emerging theory. One particularly illustrative case occurred in the North Atlantic in the latter half of the 20th century, when crews aboard container ships reported encountering 3 massive waves during storms that caused containers to break free from lashings. Subsequent investigations often focused on cargo securing practices, but wave timing was also noted. The first wave compromised stability. The second shifted cargo further. The third pushed the vessel beyond safe limits. It is worth noting that not every report of 3 large waves corresponds to the same physical mechanism. In some cases, the pattern may arise from simple observation bias. During a storm, many large waves occur. Remembering 3 in particular may reflect selective memory. However, when structural damage and instrument readings align with the narrative, the pattern gains credibility. The transition from story to science did not erase the original language. Even today, modern mariners sometimes use the phrase informally. Despite access to detailed forecasts and wave models, there remains an awareness that local conditions can produce surprises. The term Three Sisters conveys urgency efficiently. Looking back at those early accounts, what stands out is not exaggeration but consistency. Different oceans, different centuries, different ship designs, yet the description recurs. 3 unusually large waves arriving in sequence, the third often most severe. The repetition suggests that sailors were observing a real feature of complex sea states long before equations confirmed its plausibility. It is easy, from the safety of land, to underestimate how attentive mariners must be to subtle changes. A slight shift in swell direction, a tightening of wave period, the sound of impact on the hull. These details matter. They accumulate into experiential knowledge. When multiple generations describe similar patterns, it deserves attention. Scientific tools improved, researchers revisited old logbooks. They compared recorded storm conditions with modern wave models. In some cases, the descriptions aligned remarkably well with what we now understand about wave group dynamics and constructive interference. The stories were not naive. They were empirical, grounded in observation under pressure. There is also a psychological dimension to these early stories. Facing the open ocean in a storm is an intense experience. Human perception sharpens. Memory encodes dramatic moments vividly. When 3 large waves strike in rapid succession, the impression is strong. That intensity helps ensure the story is passed on accurately. Survival depends on it. Still, the sea does not follow human narrative structures. It follows physics. The fact that physics can produce patterns that fit so neatly into human storytelling is coincidental. Yet it is that coincidence that allowed knowledge to persist across centuries. In examining the first stories of the Three Sisters, we see a pattern of recognition preceding explanation. Sailors identified the hazard. They named it. They adapted behaviour accordingly. Only later did scientists begin to describe the underlying mechanisms in formal terms. As we move forward, it becomes necessary to look more closely at those mechanisms themselves. What conditions cause waves to stop behaving in ordinary ways? How does energy concentrate in such a manner that 3 crests can rise above the rest? The answers lie not in folklore, but in the detailed physics of wave interaction, wind transfer and ocean currents, where the familiar rhythm of the sea begins to shift into something less predictable. If you have ever watched waves from a shoreline on a calm day, you may have noticed how cooperative they seem. They arrive in steady intervals. Each crest resembles the one before it. The spacing feels almost measured, as though the sea has agreed to follow a quiet schedule. Even when the wind freshens and the surface grows restless, there is still a rhythm. Rise, fall, rise again. It gives the impression that waves are orderly things. That impression, however, depends on conditions being relatively simple. Out in the open ocean, especially far from land where wind has room to build strength over long distances, the surface is rarely governed by a single, tidy pattern. Instead, it is shaped by multiple wave systems layered on top of one another. Wind waves generated locally overlap with swells that may have travelled hundreds or even thousands of kilometres from distant storms. Currents move beneath them. Variations in water depth subtly alter their shape. Under these circumstances, waves can stop behaving in ways that match our expectations. To understand how this happens, it helps to return to the basic structure of a wave. A surface gravity wave forms when wind transfers energy into the ocean. The wind does not simply push the water forward, rather it creates pressure differences across small ripples. Those ripples grow, capturing more wind energy. As they increase in size, gravity acts as a restoring force, pulling the water downward. The result is oscillation. Water particles move in roughly circular paths as the wave passes. In a simplified model, waves can be described as sine curves: smooth, predictable, repeating. If all waves in the ocean followed identical sine curves, interference would still occur, but it would remain relatively easy to anticipate. Real ocean waves, however, are not identical. They vary in height, wavelength, and direction. and when many such waves overlap, the surface becomes a complex superposition of energy. Under ordinary conditions, this complexity averages out. Some waves add together briefly, others cancel each other. The overall sea state remains within expected bounds. Mariners and meteorologists use the term significant wave height, which refers to the average height of the highest one-third of waves in a given period. This provides a practical measure of roughness. It does not describe the largest individual wave, but it gives a sense of general conditions. Yet the ocean is not limited to averages. In certain situations, wave interactions become nonlinear. That means the combined effect of waves is not simply the sum of their parts. When two waves meet, their crests can align, temporarily creating a higher crest. This is constructive interference. Usually the effect is modest and fleeting. But when wave trains share similar frequencies and directions, the potential for sustained amplification increases. Imagine several wave systems travelling at slightly different speeds, but close enough in frequency that their crests periodically align. For a short interval, multiple crests overlap. The water rises higher than any single component wave would have produced alone. Then the alignment shifts, and the surface returns to more typical variation. This process can create what scientists call wave groups. Within each group, the central waves are larger than those at the edges. Wave groups are common in ocean swell. Surfers sometimes refer to sets arriving at a beach. A lull may precede a cluster of larger waves. That familiar pattern is a benign example of energy modulation. In deep water storms, the same principle can scale upward dramatically. When conditions intensify, nonlinear effects become more pronounced. A phenomenon known as the Benjamin Fair instability describes how a uniform wave train can become unstable and form localized peaks. In laboratory tanks and computer models, researchers observe that small perturbations in a wave field can grow over time. Instead of a consistent train of equal waves, clusters emerge. The central waves within those clusters can exceed the average height by a significant margin. This is one way waves stop behaving in a manner consistent with simple linear models. Another factor involves currents. When waves travel against a strong opposing current, their wavelengths shorten. Energy that was distributed over a longer horizontal distance becomes compressed. As the wavelength decreases, wave height increases. The wave steepens. If steepness exceeds a critical threshold, the crest can become unstable and break violently. Consider a storm-driven swell moving into a region where a powerful ocean current flows in the opposite direction. The Gulf Stream off the east coast of North America provides a well-documented example. Storm waves moving southward can encounter northward flowing current. The interaction increases wave height and steepness rapidly. Mariners in these areas have reported unexpectedly sharp and powerful seas, even when wind speeds alone would not suggest such severity. When multiple wave systems intersect at different angles, the surface pattern becomes even more complicated. Cross seas form, creating a grid-like arrangement of crests and troughs. In these conditions, a vessel can experience rolling from one direction while pitching from another. If wave crests from intersecting systems coincide at a specific location, a localized spike in height can occur. Bathymetry, the underwater topography of the seafloor, also influences behavior. As waves move into shallower water, they slow down. The lower part of the wave interacts with the seabed, reducing speed while the upper portion continues forward. This causes the wave to steepen. While this effect is commonly associated with coastal breaking waves, it can also occur over underwater ridges or banks in deeper water. Sudden changes in depth can concentrate wave energy unexpectedly. In storm conditions, wind input continues to pump energy into the sea surface. Gusts create variations in pressure that reinforce certain waves more than others. The sea state becomes dynamic, constantly adjusting. Most of the time, this leads to chaotic but statistically predictable variation. Occasionally, however, alignment persists long enough to produce extreme crests. The ocean does not need to create a single towering wall of water to be dangerous. It can produce a sequence of elevated crests within a short time frame. For a vessel encountering such a sequence, the difference between expected and actual conditions can be stark. There is also a role for randomness. Even in a purely linear wave field, statistical extremes are inevitable over sufficient duration. Given enough waves, some will exceed the average significantly. In nonlinear conditions, the probability of such extremes increases. The distribution of wave heights develops what statisticians call a heavy tail. That means rare, very large waves occur more often than a normal distribution would predict. In practical terms, this undermines confidence in simple forecasts. A storm predicted to generate 10-metre significant waves might also produce individual waves of 15 or 20 metres under certain interactions. If 3 of those occur close together, the effect can resemble a coordinated assault, though it is simply the outcome of overlapping physical processes. For ships, timing is critical. After climbing one large wave, a vessel begins descending into the trough. The hull experiences bending stresses. Water may wash across decks. If another large crest arrives before the ship has stabilised, dynamic forces compound. The third arrival in quick succession may meet a vessel already angled or weakened by shifting cargo. When waves behave within expected ranges, naval architecture provides sufficient margin. Hulls are designed to flex without fracturing. Stability curves ensure that moderate heel angles can be corrected by buoyancy forces. But extreme, clustered impacts approach the limits of those calculations. Breaking waves add another dimension. When a crest becomes too steep, it collapses forward. The resulting impact can generate pressures far exceeding those from non-breaking waves. Measurements indicate that breaking wave impacts can produce localized forces capable of damaging even reinforced structures. If multiple breaking crests occur in sequence, cumulative stress increases significantly. In some cases, atmospheric pressure changes associated with intense storms can temporarily lower sea surface levels beneath the eye of a low-pressure system. Surrounding water may then surge inward. Combined with wind-driven waves, this can create highly irregular surface conditions. The complexity grows further when storm systems overlap or when residual swell from a previous storm interacts with a developing one. Modern computer simulations attempt to model these interactions in detail. Using spectral wave models, researchers input wind fields, currents, and bathymetry to predict sea states. These models are increasingly accurate at large scales, yet fine-scale alignment of crests remains inherently difficult to forecast precisely. The ocean's surface at any moment represents the sum of countless interacting components. When waves stop behaving in familiar patterns, it is not because the ocean has changed its fundamental laws. It is because conditions have shifted into a regime where nonlinear amplification dominates over averaging effects. Small variations grow rather than dissipate. Alignment persists briefly rather than dispersing. From the deck of a ship, the shift can feel sudden. One moment the vessel rides a heavy but manageable swell. The next, the horizon steepens. The bow climbs higher than anticipated. The interval between crests shortens. There is less time to react. The pattern no longer feels steady. Sailors describe such moments as the sea becoming confused. In a sense, that description captures the overlap of multiple wave directions and periods. The confusion is mathematical rather than emotional. It reflects interference, energy compression, and dynamic instability. In the context of the Three Sisters, this behavioural shift sets the stage. A sea state that has entered nonlinear amplification can produce groups of large waves. Within those groups, timing determines impact severity. The first wave may surprise, the second may destabilise, the third may exceed design thresholds. It is tempting to think of such events as rare anomalies, outliers in an otherwise predictable system. They are rare relative to calm days, but given the scale of global oceans and the frequency of storms, they occur somewhere on Earth more often than most people realise. What makes them memorable is not only their size, but their clustering. Understanding when waves stop behaving as expected requires attention to the interplay of wind, current, depth, and direction. It also requires acknowledging that simple averages conceal extremes. The sea surface is a constantly evolving energy field. Under certain alignments, it can organise itself into brief episodes of disproportionate force, and as those alignments grow more precise, the conditions that give rise to sequences like the Three Sisters become clearer, leading naturally into the question of how sailors once interpreted these sudden escalations before physics offered structured explanations. Before equations described nonlinear instability, and before satellites measured wave heights from orbit, the people who spent their lives at sea formed their understanding from observation, repetition, and survival. They did not have spectral wave models. They had memory. They did not calculate probability distributions. They counted what happened and adjusted their behaviour accordingly. When waves behaved normally, sailors trusted experience. They learned how a vessel responded in heavy weather. They learned how to turn into a swell, when to shorten sail, how to balance cargo weight. But when something outside routine occurred, when 3 unusually large waves arrived in rapid succession, they had to interpret it using the language available to them. It is easy, from a modern perspective, to assume that pre-scientific explanations were mostly superstition. Certainly, superstition existed. The sea has always encouraged symbolic thinking, but most working sailors were practical. A captain responsible for cargo and crew did not survive long by mistaking physics for spirits. Even when they lacked formal theory, they sought patterns grounded in experience. Logbooks from the 17th and 18th centuries reveal careful notations about sea state. Phrases such as "encountered 3 heavy seas in close order" appear in multiple archives. The descriptions often include practical consequences: damaged rigging, water shipped over the bow, broken spars. Rarely do they attribute such sequences directly to divine intervention. Instead, they mark them as unusual and dangerous features of the storm. In northern waters, especially among Scandinavian and Scottish fishing communities, the Three Sisters were spoken of as a warning pattern. The advice passed between crews was simple: brace after the first heavy sea, expect 2 more. This was not mysticism, it was instruction shaped by repetition. Fishermen learned that the first large wave often signalled a grouping rather than an isolated anomaly. Some sailors interpreted the pattern as part of the storm's structure. Without using the term wave packet, they observed that storms seemed to breathe. Periods of relative lull were followed by bursts of greater intensity. Within those bursts, several larger waves clustered together. The count of 3 may have been partly perceptual, but it also reflected the common size of prominent clusters. There were also regional variations in interpretation. In the North Atlantic, the Three Sisters were associated with deep water storms. In coastal regions with shallow seabeds, the pattern was linked to sandbanks and underwater ridges. Mariners noticed that certain areas produced more chaotic seas than others. Without bathymetric charts as detailed as those we have today, they relied on accumulated knowledge of where waves tended to steepen unexpectedly. The Southern Ocean, where strong winds circle Antarctica with minimal land interruption, earned a reputation for relentless wave trains. Sailors rounding Cape Horn often described sequences of massive swells that felt almost organised. Some logs speak of 3 towering seas that struck as one intent. The wording reflects the intensity of the experience, but the recurrence of grouped waves appears consistently. Even in the Pacific, among Polynesian navigators who mastered ocean swells long before European exploration, knowledge of wave grouping existed in a different form. These navigators read subtle variations in swell patterns to determine direction and proximity to islands. While they may not have used the specific term Three Sisters, they understood that wave energy often arrived in structured sets rather than uniform repetition. On merchant vessels of the 19th century, captains developed rules of thumb for handling grouped seas. If the first heavy wave broke over the forecastle, orders were often given immediately to secure hatches and reduce forward exposure. there was an implicit assumption that additional large waves would follow. The pattern recognition did not require mathematics, it required attention. At the same time, sailors were cautious about overconfidence. The sea could mislead. Sometimes a single enormous wave would strike without obvious companions. Other times, a group of 2 might arrive instead of 3. The number was less important than the clustering itself. But the repetition of 3 in narrative likely reflects how strongly that sequence impressed itself on memory. Human cognition favours patterns. 3 events form a sequence that feels complete. It is possible that in storms producing 4 or 5 large waves in succession, the first 3 were remembered most clearly. Yet structural damage reports often align with the description of multiple heavy impacts in quick order, lending credibility to the observed clustering. Superstition did intertwine with observation in certain contexts. Some sailors believed that the 3 sisters were assigned to change course or reduce speed. In that sense, the pattern became a trigger for action. The belief itself may have been coloured by folklore, but the behavioural outcome often improved safety. Anticipating additional waves encouraged readiness. There were also cases where the phenomenon was framed as a test. Maritime culture frequently emphasised endurance. A crew that weathered 3 massive seas in succession was seen as having proven competence. The narrative reinforced identity, yet even here, the focus remained practical. Survival through the sequence mattered more than its symbolic meaning. As steel ships replaced wooden hulls, interpretations evolved but did not disappear. Engineers and captains noted that grouped waves could induce severe hull stress, before full understanding of hogging and sagging stresses was widespread. Sailors recognised that ships flexed visibly under heavy seas. The arrival of several extreme waves back to back increased anxiety about structural integrity. In some naval traditions, training manuals began to incorporate warnings about clustered waves even before formal nonlinear wave theory was widely accepted. Experience at sea shaped guidance. Cadets were taught that extreme seas often travelled in sets. The number 3 persisted in oral instruction because it was concise and memorable. It is important to acknowledge that not all early interpretations were accurate. Without precise measurement tools, wave heights were estimated visually. Fear can amplify perception. A 15-metre wave might be remembered as 20. However, even when magnitudes were overestimated, the clustering itself remained a consistent theme. During the early development of oceanography in the late 19th century, some scientists dismissed reports of extraordinary waves as exaggeration. The prevailing statistical models suggested that waves significantly exceeding average heights were nearly impossible. Sailors who insisted otherwise were sometimes viewed as unreliable narrators. Yet the sea does not adjust itself to fit theoretical convenience. As more instrumented platforms were deployed in the 20th century, data began to reveal that extreme waves, while rare, were real. And in some cases, instrument records showed multiple high peaks occurring within short time windows, consistent with the long-standing accounts of grouped waves. This alignment between story and data is notable. It suggests that practical seafaring knowledge had identified a genuine phenomenon even without formal explanation. Sailors thought in terms of sequences because that is how the danger presented itself. They did not need to understand constructive interference to know that a first heavy impact might be followed by 2 more. In examining what sailors thought before science did, it becomes clear that their interpretations were rooted in necessity. They developed working models. Those models may not have been expressed in equations, but they were refined through repeated exposure to harsh conditions. There is also a psychological dimension to their thinking. When facing immense forces beyond direct control, assigning structure can reduce uncertainty. Naming a pattern makes it manageable. The term 3 sisters condensed complexity into a clear warning. Whether the number was exact or approximate mattered less than the message it conveyed. The first extreme wave is not always the last. In many cases, sailors describe the 3rd wave as the most dangerous. That perception may reflect the cumulative effect of damage and fatigue. After 2 severe impacts, crew readiness decreases. equipment may already be compromised. The third impact arrives when resilience is lowest. This experience likely reinforced the narrative emphasis on the final wave. Interestingly, even in modern times, experienced mariners sometimes speak of the sea in relational terms, not because they reject science, but because language shaped by centuries of seafaring remains efficient. Saying "watch for the sisters" communicates more quickly than reciting hydrodynamic theory. As science advanced, it did not erase these earlier interpretations. Instead, it layered explanation onto them. Nonlinear wave theory, spectral analysis, and satellite measurements provided mechanisms. But the pattern had been recognized long before the mechanisms were described. In that sense, sailors were not wrong. They lacked vocabulary for interference and instability, yet they correctly identified a recurring feature of storm-driven seas. Their thoughts were pragmatic. They saw what happened. They adapted. They passed on what they learned. And as we move from their interpretations toward a closer examination of the physical structure of a single wave, it becomes clear how those practical observations connect directly to the underlying mechanics that allow multiple crests to align and rise beyond expectation. Before several waves can combine into something dangerous, before timing and interference complicate the picture, it helps to slow down and look carefully at just one, a single wave, not a sequence, not a storm system, just one oscillation moving across the surface of the sea. At first glance, a wave appears simple. A crest rises, a trough follows. The water seems to move forward, then disappear beneath the next crest. From a distance, it resembles a travelling wall. But if you could freeze the motion and look at what the water particles are actually doing, the picture would change. In deep water, a surface gravity wave does not carry the water itself across the ocean. Instead, it carries energy. The water particles move in circular orbits. As the wave crest approaches, a particle near the surface rises and moves slightly forward. As the crest passes, the particle descends and moves slightly backward. After the wave has passed completely, the particle returns almost to its original position. What travels forward is not the water, but the oscillation. This distinction matters, because when we talk about waves adding together, growing taller, or becoming unstable, we are describing the behaviour of energy within a moving field, not the mass of water itself marching forward like a solid object. The simplest mathematical description of a wave is a sine curve, smooth, periodic, predictable. In that idealized form, the wave has a wavelength, which is the horizontal distance between successive crests. It has a period, which is the time between crests passing a fixed point, and it has an amplitude, which is half the vertical distance from crest to trough. Double the amplitude and you double the wave height. In deep water, wavelength and period are related through gravity. Longer waves travel faster. This relationship is called dispersion. A swell generated by a distant storm can travel thousands of kilometres, and as it moves, its shorter components slow down and fall behind, leaving longer waves to dominate. That is why swell arriving on a coastline after a storm far away often feels orderly and long period, even if the storm itself was chaotic. Wind waves behave somewhat differently, because they are actively being fed energy by wind. When wind blows across the ocean's surface, it transfers momentum to the water. The strength of the wind, the duration of its blow, and the distance over which it acts all influence the resulting wave size. Strong winds sustained over long fetches create larger waves. At the start, small ripples form. These ripples increase the surface roughness, making it easier for wind to grip the water. The ripples grow into waves. As waves grow taller, gravity pushes downward, resisting further growth. A balance develops between wind input and gravitational restoring force. That balance defines the typical wave height under given conditions. In linear wave theory, which is a useful first approximation, waves pass through one another without altering each other's shape. Two waves crossing paths simply superimpose. Where their crests align, they add. Where a crest meets a trough, they subtract. After crossing, each wave continues unaffected. This is a convenient simplification and works reasonably well for small amplitude waves. However, the ocean rarely confines itself to small amplitudes. As wave height increases relative to wavelength, nonlinear effects emerge. The crest becomes sharper, the trough becomes broader, the particle orbits become slightly distorted. The forward motion at the crest exceeds the backward motion in the trough. This asymmetry introduces subtle net transport known as Stokes drift. While small, this drift contributes to the overall movement of surface water over time. More importantly for extreme events, nonlinearity changes how waves interact. In nonlinear conditions, waves do not simply pass through each other unchanged. Energy can be transferred between components. Certain frequencies can grow at the expense of others. Small perturbations in a uniform wave train can amplify. The steepness of a wave is a critical parameter. It is defined as the ratio of wave height to wavelength. When steepness exceeds a threshold, the crest becomes unstable. The water at the top moves faster than the wave itself and begins to spill forward. This is braking. Braking dissipates energy, but before it does, it can release immense force. Wave breaking is familiar near shorelines, but in deep water storms, braking can occur as well. The difference is scale. Offshore breaking waves can be far larger and more forceful. The impact pressure when a breaking crest strikes a structure can be several times greater than that of a non-breaking wave of the same height. Now consider the internal structure of a wave. Beneath the surface, motion decays exponentially with depth. At a depth equal to roughly half the wavelength, particle motion becomes negligible. This means that long-period waves influence water movement deeper than short-period waves. In storm conditions, long swells generated by distant systems may interact with shorter, locally generated waves, creating layered motion. The energy carried by a wave is proportional to the square of its amplitude. That means doubling the height increases energy fourfold. A modest increase in height represents a much larger increase in force potential. When thinking about extreme seas, this quadratic relationship is crucial. A wave twice as tall is not merely twice as powerful. The pressure exerted by a wave on a ship hull depends on multiple factors. Hydrostatic pressure increases with depth, but dynamic pressure from moving water adds to it. When a crest impacts a hull, the deceleration of water generates force. The faster and steeper the wave, the greater the force. Ships are designed to handle expected wave loads. Engineers use models to estimate bending moments along the hull. When a wave supports the bow and stern but leaves the midsection unsupported, the hull experiences hogging stress. When the midsection is supported and the ends hang over troughs, sagging stress occurs. A single large wave can produce one of these stress states. But understanding a single wave's mechanics helps explain how repeated stresses accumulate. There is also the matter of group velocity. While individual crests move at a certain speed, the envelope of a wave group travels at half that speed in deep water. This distinction is subtle but important. Energy propagates at group velocity. When energy clusters within a group, the most intense waves are found near the centre of that moving envelope. Even in a single wave, local irregularities exist. Wind gusts can temporarily increase crest height. Surface tension plays a role at very small scales. Turbulence in the upper water column can distort shape. The ocean surface is never a perfectly smooth mathematical function. If we examine a single large storm wave, perhaps 15 meters high, we see a structure shaped by the wind field that created it. The crest may lean forward. The face may be smooth or streaked with foam. The period might be 10 to 15 seconds. Beneath it, particles move in large circular paths near the surface, shrinking with depth. When such a wave passes under a ship, the vessel rises on the crest. As it moves toward the trough, the hull angles downward. The rate of change in vertical acceleration matters as much as the height itself. A steep, fast-rising wave can create sharp accelerations that stress structural components. Now imagine increasing the height modestly, perhaps to 20 meters, while keeping wavelength similar. Energy increases dramatically, steepness increases, the likelihood of breaking grows, impact forces scale accordingly. Understanding a single wave's behavior lays the foundation for understanding what happens when several waves interact. If each wave carries energy proportional to the square of its amplitude, and if alignment allows amplitudes to add temporarily, the resulting crest can be significantly larger than its components. This is where the transition from single-wave physics to multi-wave amplification begins. The ocean does not generate waves randomly in isolation. It generates spectra of waves, each with its own amplitude and frequency. The behavior of one wave cannot be fully separated from the others, yet examining one in detail clarifies the mechanisms at work. In calm conditions, single-wave theory provides a close approximation. In storms, where amplitudes grow and interactions intensify, linear assumptions weaken. A single wave becomes part of a larger dynamic network, and as we move from the physics of one oscillation to the interaction of several, the question naturally shifts toward what happens when three significant crests align, not just spatially, but temporally, forming a sequence that challenges even the strongest hulls. A single large wave is powerful. Two in succession can test balance, but when three significant crests arrive with just the right spacing, something changes. The danger is no longer confined to height alone. It becomes a matter of timing, accumulated stress, and the way energy organizes itself across the sea surface. To understand how three waves become one threat, it helps to picture not isolated crests, but a moving field of energy. In storm conditions, waves rarely travel independently. They move in groups. Within each group, several waves are taller than those around them. The grouping itself is the result of interference between wave components with similar frequencies. Imagine a long train of waves moving across the ocean. Some components have slightly shorter periods, others are slightly longer. As they travel, their phases shift relative to one another. At certain points, several crests align. This alignment does not last forever. It builds, peaks, and fades. But during the peak, the sea surface rises above what any single component would produce on its own. If the central portion of that group contains three particularly strong crests, separated by regular intervals, a vessel encountering them experiences a sequence that feels coordinated. The first crest lifts the bow sharply. The ship begins to descend into the trough. Before it has stabilized, the second crest arrives. The third follows while the vessel is still reacting to the previous two. The threat lies in how the ship responds to dynamic loading. A vessel at sea is never static. It moves in 6 degrees of freedom: heave, pitch, roll, surge, sway, and yaw. In heavy seas, pitch and roll dominate. A large head-on wave causes pitching. A wave striking at an angle induces roll. Recovery from these motions takes time. The hull flexes. Cargo shifts slightly within its restraints. Water may collect on deck before draining away. When three waves arrive close together, recovery time shortens. The vessel may still be climbing out of one trough when the next crest lifts it again. Structural stresses that might have dissipated between isolated impacts instead overlap. If the second wave strikes while the hull is already bending, the resulting stress state can approach or exceed design limits. There is also resonance to consider. Every ship has natural frequencies of motion. If incoming waves match or approach those frequencies, motion amplitude increases. In a sequence of three waves with similar period, resonance effects can amplify pitching or rolling. The first wave initiates motion, the second reinforces it. The third arrives when motion is already significant. This is not a theoretical curiosity. In structural engineering, repeated loads can cause fatigue. Material subjected to cyclic stress weaken over time. Although three waves alone do not create long-term fatigue, the immediate cyclic loading can produce peak stresses greater than a single static load of similar magnitude. Wave steepness plays a role as well. In severe conditions, crests may become steep enough to break. A breaking crest impacts with greater force than a smooth one. When 3 steep waves break in sequence, impact pressures can be extreme. The first may damage fittings, the second may compromise watertight integrity. The third may exploit that weakness. Timing is central. If the period between waves is 10 seconds, 3 waves arrive within half a minute. For a large vessel in heavy seas, 30 seconds can feel brief. The first impact may throw crew off balance. Securing equipment takes time. Adjusting course requires engine response. By the time corrective measures begin, the second wave may already be rising. The sea does not arrange these sequences deliberately. They arise from group dynamics in the wave field. The envelope of a wave group moves at group velocity. Within that envelope, crests increase and decrease in amplitude. The highest crests cluster near the centre. When a ship intersects that centre, it experiences several high crests before the envelope passes. Mathematically, this can be described using modulation theory. A primary wave train becomes modulated by a lower frequency envelope. The envelope's peak corresponds to the cluster of highest waves. Depending on the width of the envelope, several significant crests may occur within it. 3 is common, though not exclusive. In deep water storms, wave groups can span hundreds of meters. The highest waves within them may be separated by consistent wavelengths. For a ship whose length is comparable to that wavelength, positioning relative to crest and trough becomes critical. If the first crest lifts the bow while the stern is still in a trough, hogging stress develops. If the second crest supports midship while ends are unsupported, sagging stress follows. Rapid alternation increases structural demand. The cumulative effect of 3 waves differs from that of 1 even if their individual heights are similar. Consider the first wave raising the vessel to a steep pitch angle. The hull experiences bending. Water may slam against the forward deck. Before the structure fully relaxes, the second crest increases pitch further or reverses it abruptly. The third wave may strike at the moment of maximum stress from the previous motion. Cargo vessels are particularly sensitive to longitudinal bending moments. Large container ships, for example, can be over 300 meters long. When spanning a trough between 2 crests, the midsection is unsupported. If a following crest lifts the midsection before the ends settle, stress reverses quickly. Repeated reversals increase peak bending. Bulk carriers and tankers also face risks from sloshing effects within partially filled tanks. When subjected to rapid pitch and roll, liquid cargo can shift violently. If 3 waves induce strong oscillations, internal fluid motion may amplify structural stress. Fishing vessels, being smaller, face different but equally serious threats. For them, freeboard is lower. A large breaking wave can wash across deck space more easily. The first wave may flood working areas. The second can destabilize further. The third may overwhelm pumping capacity or reduce buoyancy sufficiently to capsize. There is also the psychological factor aboard any vessel. After a severe impact, crew members react. Orders are shouted, adjustments are made. The human system is processing the event. If 2 more impacts follow immediately, decision-making may lag behind events. In extreme conditions, seconds matter. Wave direction relative to vessel heading influences severity. A head-on encounter maximizes pitch. A beam encounter maximizes roll. Quartering seas introduce complex combined motion. In a group of 3 waves, slight directional variations between crests can compound instability. The first may induce pitch. The second may add roll. The third arrives when the vessel is misaligned. Modern vessels rely on forecasts to avoid severe storms, yet avoidance is not always possible. Cargo schedules, fuel considerations, and storm development speed all influence routing decisions. Even with careful planning, ships can encounter conditions where wave grouping intensifies unexpectedly. Instrument measurements from offshore platforms have shown sequences of large waves occurring within short windows. While not always exactly 3, clusters of 2 to 5 elevated crests are documented. In some cases, the highest wave in a group exceeds twice the significant wave height. If 3 such waves occur consecutively, the cumulative effect resembles the long-reported Three Sisters pattern. Energy concentration is key. Because wave energy scales with the square of amplitude, a modest increase in height dramatically increases force potential. If 3 waves in a group are significantly taller than average, the energy delivered over that short interval is disproportionately large. Braking adds yet another layer. Impact pressures from plunging breakers can exceed static hydrostatic pressure by several multiples. When repeated in quick succession, local structural damage can escalate. Windows on bridge decks have been shattered by extreme breaking waves. Hatches have been forced inward. If the first breaker compromises a seal, subsequent ones exploit the weakness. The sea surface between groups may return to more typical heights. After 3 severe waves, there may be a relative lull. This contrast can reinforce the perception of distinct grouping. For the crew, surviving the cluster may feel like emerging from an attack. From a physical standpoint, nothing supernatural has occurred. Interference, modulation, resonance, and steepness have combined in a brief alignment. The ocean's energy field organized itself momentarily into a configuration that maximized local amplitude and impact timing. The important realization is that the threat lies not solely in the maximum height of a single crest, but in the way multiple high crests interact with vessel dynamics. The first destabilizes, the second compounds, the third tests structural and operational limits. As understanding deepens, it becomes clear that these sequences are closely related to a broader phenomenon that once seemed impossible to scientists, the rogue wave. And examining that connection brings us naturally toward the study of singular walls of water that rise beyond expectation in open seas. There was a time, not very long ago, when the idea of a single wave towering far above all others in open ocean was treated with skepticism. Sailors had described them for generations. They spoke of walls of water appearing without warning, rising steep and dark against the horizon. These waves were said to dwarf the surrounding sea, to strike with explosive force, and then vanish back into the general storm pattern as if nothing unusual had happened. For years, many scientists regarded these accounts as exaggeration. Instruments rarely recorded such extremes, and statistical models suggested they were nearly impossible. But the ocean does not consult probability tables before it acts. In January 1995, an offshore platform in the North Sea known as Draupner recorded something that shifted the conversation permanently. During a winter storm, a wave measuring approximately 25.6 meters in height struck the platform. The surrounding significant wave height was far lower. The instruments were calibrated. The data was verified. The wave was real. It was not part of a gentle progression upward. It was a sudden spike, a crest that rose far above its neighbours. This event did not invent rogue waves, it confirmed them. A rogue wave, in modern oceanographic terms, is typically defined as a wave whose height is more than twice the significant wave height of the surrounding sea state. That means if the average of the highest third of waves is, for example, 10 metres, a rogue wave would exceed 20 metres. It is not simply a large wave. It is disproportionately large compared to what statistics predict. What makes rogue waves particularly dangerous is not only their size, but their isolation. They often appear as singular events. A ship may be riding heavy but manageable seas when suddenly a single crest rises sharply ahead. There is little time to prepare. The wave face may be steep, nearly vertical. It can resemble a moving cliff rather than a rolling swell. To understand how such a wave forms, we must return to the physics of wave interaction. As discussed earlier, the ocean surface is a superposition of many wave components with different frequencies and directions. In linear theory, these components simply add together temporarily and then continue on their way. But in nonlinear regimes, energy can concentrate in ways that amplify certain crests far beyond the average. One mechanism involves constructive interference. If multiple wave components align in phase at the same location, their amplitudes add. This can create a temporarily elevated crest. Usually such alignment is brief and moderate. But when many components share similar frequencies and directions, the probability of significant alignment increases. Another mechanism is modulation instability, also known as the Benjamin-Fair instability. In this process, a uniform wave train becomes unstable, and energy transfers into localized peaks. Laboratory experiments and numerical simulations show that under certain conditions, small perturbations in wave amplitude can grow exponentially. Instead of a consistent pattern of similar waves, a dominant crest emerges within a group. Current interactions further complicate matters. When waves travel into opposing currents, their wavelengths shorten and heights increase. In regions where strong currents meet storm-driven waves, such as near the Agulhas Current off South Africa, or the Gulf Stream in the North Atlantic, rogue waves have been reported with unusual frequency. The compression of wave energy by opposing flow enhances steepness and increases the likelihood of extreme peaks. Wind also plays a role beyond initial generation. Strong gusts can inject additional energy into an already amplified crest, pushing it higher. The combined effect of nonlinear interaction, current compression, and wind input can produce a wave that rises sharply above its surroundings. From the perspective of someone on a ship, a rogue wave can appear with startling suddenness. The horizon may tilt upward as a steep wall approaches. Unlike long swells that lift gradually, a rogue crest may rise abruptly with a short, steep face. The vessel may not have sufficient time to align properly. If struck broadside, rolling can be severe. If taken head-on, pitching accelerations can be extreme. The structural consequences can be significant. Bridge windows have been shattered by rogue waves. Containers have been swept from decks. Even large vessels have reported bow damage from impact forces exceeding design assumptions. The forward sections of ships are especially vulnerable because they meet waves directly. Rogue waves are often described as isolated, but isolation is relative. They arise within a complex sea state. The surrounding waves may still be large, but the rogue stands out dramatically. Its crest-to-trough height exceeds expectations. Its steepness may approach the breaking limit. It is important to note that rogue waves are not tsunamis. Tsunamis are generated by seismic events and have extremely long wavelengths. In deep water, they may be barely noticeable. Rogue waves are wind-generated and occur in deep ocean storms. They are surface phenomena shaped by atmospheric and oceanic dynamics. Measurement technology has improved dramatically since the Draupner event. Satellite radar altimeters scan wide swathes of ocean surface, detecting wave heights across global scales. These measurements confirm that rogue waves occur more frequently than once believed. They are rare relative to total wave count, but given the vastness of the ocean, they are not exceedingly uncommon. The connection between rogue waves and the Three Sisters becomes clearer when we consider grouping. A rogue wave may form at the centre of a wave group. If that group contains several high crests, the rogue may be accompanied by other large waves in close succession. In some cases, what sailors describe as three massive waves may include one rogue-level crest flanked by slightly smaller but still extreme companions. The sudden wall-like appearance of rogue waves is partly due to steepness. As amplitude increases relative to wavelength, the crest sharpens. The front face becomes steeper. In extreme cases, the wave may lean forward. The visual effect is striking. Unlike a gently sloping swell, the rogue's face can resemble a vertical incline. There is also a matter of relative scale. In a storm where surrounding waves are already 10 or 15 metres high, a 25-metre crest does not simply add 10 metres of difference. It alters the geometry of encounter. A ship that could comfortably ride 10-metre swells may struggle with a crest more than twice that height. Braking behaviour amplifies the threat. When a rogue wave breaks, it releases concentrated kinetic energy. The plunging water mass can strike with force comparable to a moving wall of concrete. Localized impact pressures can exceed hundreds of kilopascals. Such forces can deform steel plating or compromise superstructures. Rogue waves challenge assumptions about statistical limits. For many years, engineers relied on linear wave models that predicted maximum heights based on Gaussian distributions. These models underestimated the frequency of extreme outliers. Nonlinear models and heavy-tailed statistical approaches now provide better estimates, but uncertainty remains. For mariners, the knowledge that rogue waves exist changes perception. Even in heavy but steady seas, there is awareness that a singular extreme event is possible. Vigilance increases. Bridge crews monitor radar returns and wave patterns closely, yet detection is difficult. A rogue wave may not be distinguishable from surrounding seas until it is already close. There are ongoing research efforts to improve prediction. Some approaches involve real-time wave field analysis using radar mounted on ships or platforms. By measuring the phase relationships of incoming waves, algorithms attempt to identify growing peaks before they fully form. Early detection could allow course adjustment or bracing procedures. However, the practical time window for reaction is often short. The physics underlying rogue waves also appears in other fields. Similar nonlinear wave amplification has been observed in optics, plasma physics, and even financial markets, where extreme spikes occur in systems characterized by interacting components. The mathematics of modulation instability applies broadly wherever waves or oscillations interact. Despite scientific advances, the experience of encountering a rogue wave remains deeply physical. The sudden rise, the impact, the spray driven across decks, the sense that the sea has momentarily exceeded its usual bounds. These experiences leave strong impressions. There are recorded incidents where ships have reported a single massive wave striking, and then conditions returning to prior levels. In other cases, multiple large waves followed within minutes. The variability reflects the underlying complexity of sea states. One notable incident involved the cruise ship MS Bremen in 2001, which encountered a rogue wave in the South Atlantic that shattered bridge windows and temporarily disabled navigation equipment. The wave was estimated at over 30 meters. The ship survived, but the event underscored the vulnerability even of large, modern vessels. Such events reinforce the connection between rogue waves and clustered wave sequences. When energy concentrates strongly in one location, it may not dissipate instantly. Nearby crests within the same group may also be elevated. The distinction between a singular rogue and a short sequence of extreme waves becomes blurred. The ocean's sudden wall is therefore not entirely isolated from the broader wave field. It is an expression of the same processes that can produce three large waves in succession. In some cases, the Three Sisters pattern may include a rogue wave at its centre. In others, all three waves may fall below the strict rogue definition, yet still exceed design expectations significantly. Understanding rogue waves reshapes how we think about ocean risk. It highlights the limitations of average-based forecasting. It emphasizes the importance of nonlinear dynamics, and it reminds us that even in a system governed by physical laws, extremes can emerge abruptly. The study of rogue waves continues to evolve. Improved measurement networks, advanced simulations, and interdisciplinary research contribute to clearer models. Yet complete prediction remains elusive. The ocean is too vast and too dynamic for precise, location-specific forecasts of singular crests. For ships crossing open water, preparation remains the primary defence. Structural reinforcement, watertight integrity, cargo securing protocols, and route planning all reduce vulnerability. But the possibility of encountering a sudden, towering crest remains part of seafaring reality. And when we place that reality alongside the phenomenon of grouped waves arriving in close succession, the line between singular rogue and clustered threat grows increasingly thin, guiding us toward a deeper examination of how interference and energy amplification operate within the mathematics of the sea itself. If the ocean were made of a single wave repeating endlessly, its behaviour would be easy to predict. But the sea is not one oscillation. It is a layered system of countless waves, each with its own height, wavelength, direction, and phase. When these waves overlap, they do not politely avoid one another. They combine, and sometimes they combine in ways that produce results far larger than expected. To understand how amplification occurs, we have to slow down and examine interference carefully. Interference is simply what happens when two or more waves occupy the same space at the same time. Because waves are oscillations, they can add together or subtract from one another, depending on how their crests and troughs align. In its simplest form, constructive interference occurs when two crests meet. If one wave has a height of 5 meters and another has a height of 5 meters, their combined crest can momentarily reach 10 meters. This doubling is temporary. As the waves move forward, they separate and return to their original forms. But in that brief alignment, amplitude increases. Destructive interference is the opposite. A crest meeting a trough can reduce the surface height locally. In a chaotic sea state, both constructive and destructive interference are constantly occurring. Most of the time, these effects average out. The key word there is most. When many waves share similar frequencies and travel in roughly the same direction, the probability of extended constructive interference rises. Imagine multiple wave trains, each with slightly different periods, but close enough that their peaks occasionally synchronize. Instead of a brief doubling between two waves, you may have 3, 4 or more contributing to a single crest. Now consider energy. The energy carried by a wave is proportional to the square of its amplitude. This is not a casual detail. If amplitude doubles, energy increases by a factor of 4. If amplitude triples, energy increases 9-fold. Amplification is therefore not linear in consequence. A modest increase in height can represent a dramatic increase in energy density. In a storm, the ocean surface becomes a spectrum of waves. Scientists often describe this using a wave energy spectrum, which shows how energy is distributed across different frequencies. The sea is not dominated by one clean frequency, but by a band of them. When energy concentrates within a narrower band, wave groups become more pronounced. Group formation can be described mathematically using modulation theory. If we take a primary wave with a given frequency and introduce slight variations, we create what is known as an envelope. The envelope modulates the amplitude of the primary wave. At the peak of the envelope, amplitude is highest. At its trough, amplitude diminishes. This envelope travels at group velocity. Within it, several waves reach elevated heights. When the envelope's peak passes a ship, it may encounter 3 or more large crests in close succession. The mathematics governing this behaviour arises from solutions to the nonlinear Schrödinger equation, which describes how wave packets evolve in dispersive media like deep water. Dispersion itself is essential. In deep water, longer waves travel faster than shorter ones. This means that over time, waves of different frequencies separate spatially. But when wind continuously injects energy, and when frequencies cluster closely, separation is limited. Interaction persists. Nonlinear interaction is what allows small perturbations to grow. In linear theory, a slight irregularity would remain small. In nonlinear systems, energy can transfer from sideband frequencies into a central peak. The Benjamin-Fair instability demonstrates how a nearly uniform wave train can become unstable and produce localized amplification. Laboratory experiments have shown this clearly. Researchers generate a controlled wave train in a tank. Initially, waves are nearly identical. Then small modulations are introduced. As the wave train travels, these modulations grow. The central wave within a group becomes significantly taller than its neighbours. The process is not random. It follows predictable equations. Yet its outcome is a sharp spike in amplitude. In the open ocean, additional complexity arises. currents modify wave speed. If a wave moves into an opposing current, its wavelength shortens. Since energy is conserved over shorter horizontal distance, amplitude increases. This compression effect can intensify amplification processes already underway. Directional spreading also matters. When waves travel in slightly different directions, their interference patterns form complex grids. At certain intersection points, multiple crests align both temporally and spatially. These localized alignments can produce peaks significantly larger than the surrounding sea. The mathematics does not require intention. It requires phase alignment. Phase refers to the position of a wave within its cycle. When several waves share phase alignment at a specific point, amplitude adds. When alignment extends across several cycles within a group, the effect persists for multiple crests. This persistence is critical for understanding sequences like the Three Sisters. A single constructive interference event may produce one unusually large crest. But if the envelope is broad enough, 3 consecutive crests within it may all exceed the average significantly. Let us consider a simplified numerical example. Suppose the significant wave height in a storm is 10 meters. Individual component waves range from 6 to 12 meters. Now imagine 3 wave components with amplitudes slightly above average, aligned constructively within a group. Their combined crest may reach 15 or even 20 meters. If the envelope maintains high amplitude across 3 cycles, 3 crests in a row may reach similar heights. Because energy scales with amplitude squared, the energy density at the peak crest can be several times higher than the average sea state. The forces exerted on a vessel encountering this crest increase accordingly. Another layer of amplification arises from steepness. As amplitude grows relative to wavelength, the wave profile becomes asymmetric. The crest sharpens and may lean forward. Nonlinear, steepening increases local water velocity at the crest. If crest velocity approaches wave speed, instability and braking occur. Braking releases concentrated energy and increases impact force. Mathematics describes this threshold in terms of steepness parameters. There is a critical ratio beyond which the wave becomes dynamically unstable. In natural sea states, approaching that threshold often coincides with interference-driven amplification. The same processes that elevate amplitude also increase steepness. Energy flux across the ocean surface can therefore fluctuate dramatically over short spatial and temporal scales. A vessel passing through a region of average wave energy may suddenly enter a zone where the local energy density is several times higher due to constructive interference and modulation. From a statistical standpoint, this produces heavy-tailed distributions. Rather than wave heights clustering tightly around a mean value, the probability of extreme outliers increases. Standard Gaussian assumptions underestimate the frequency of these extremes. Modern wave statistics incorporate nonlinear corrections to account for this. There is also a feedback effect. As waves amplify, they alter local flow patterns. Increased turbulence and surface roughness can modify wind input slightly. While these effects are small relative to primary energy sources, they contribute to the complexity of amplification dynamics. The ocean is therefore not merely a random superposition of independent waves, it is a non-linear dynamical system. Energy transfers between components. Phase relationships evolve. Under certain conditions, energy concentrates into localized peaks. These localized peaks can manifest as rogue waves or as clusters of unusually large waves. When 3 such peaks occur within the same envelope maximum, the result is a short sequence of elevated crests. The mathematics predicts this possibility. The sea occasionally realizes it. It is important to emphasize that amplification does not violate conservation of energy. Energy is not created from nothing, it is redistributed. Surrounding waves may temporarily diminish as energy concentrates into a central crest. The dramatic rise of one wave corresponds to subtle adjustments elsewhere in the spectrum. For a ship at sea, however, the redistribution is irrelevant. What matters is the crest encountered. The mathematics operating behind the surface is invisible from the deck. The crew experiences only the outcome. Modern computational models attempt to simulate these nonlinear interactions. High-resolution spectral models incorporate wind input, current fields, and directional spreading. They can reproduce roguelike events in simulations, yet predicting the precise timing and location of a single amplified crest remains extremely difficult. The ocean's surface evolves continuously. Small uncertainties in initial phase relationships can lead to significant differences in outcome. This sensitivity resembles other nonlinear systems in physics, where small perturbations can influence later states disproportionately. Amplification through interference is not confined to water waves. It appears in acoustics, optics, and quantum systems. Wherever waves overlap, phase alignment determines amplitude. The mathematics is universal. The ocean simply provides one of the most visually dramatic stages on which it plays out. When three waves become one threat, it is not because three independent storms have arrived simultaneously. It's because interference and nonlinear modulation have organized energy temporarily into a compact form. The crest heights increase, energy density spikes. And if a vessel intersects that spike at the wrong moment, the experience can exceed expectations set by averages alone. This mathematical foundation helps explain how a rare phenomenon can sink even giant ships. Not by constant overwhelming force, but by brief episodes of concentrated energy delivered with unforgiving timing. There is something deeply reassuring about the sight of a large ship at sea. The scale alone suggests stability. Steel hulls stretching hundreds of meters, engines powerful enough to push tens of thousands of tons through open water, bridges rising high above the surface. Compared to a small fishing vessel, a modern container ship or tanker looks immovable, yet scale can be deceptive. A large cargo ship may weigh over 200,000 tons when fully loaded. Its hull plates are thick. Its internal structure is reinforced with longitudinal and transverse frames. Designers calculate bending moments, shear forces, torsion, and impact loads. Computer simulations model extreme weather scenarios. Classification societies set safety standards. The engineering is precise. But the ocean does not negotiate with engineering margins. It applies force according to physical law. To understand why even giant ships are not safe from extreme wave events, we must examine what happens when a large vessel interacts with large waves. A ship at sea behaves like a long, flexible beam floating on a dynamic surface. It is not a rigid block. It bends, it twists, it responds to wave shape and timing. Consider longitudinal bending first. When a wave crest supports the bow and stern simultaneously, leaving the midsection in a trough, the ship experiences hogging stress. The ends are lifted while the center sags. The upper deck experiences tension. The keel experiences compression. When the situation reverses with a crest supporting the midsection and the bow and stern over troughs, the ship experiences sagging stress. The keel is in tension. The deck is in compression. Designers anticipate both scenarios. They calculate maximum expected bending moments based on statistical wave data. They apply safety factors. Still yields at known stress levels. The structure is built to withstand repeated loading within predicted limits. However, predictions rely on assumptions about wave statistics. If a wave exceeds those assumptions significantly, the resulting bending moment can approach or exceed design capacity. A single extreme wave may not break a ship outright, but it can push structural components toward their limits. Now introduce timing. If a large vessel encounters one unusually high wave, it undergoes bending. The hull flexes. After the wave passes, stress decreases as the ship settles into a trough or onto calmer surface. If another extreme wave arrives after sufficient time has passed, the structure is partially relaxed. But when multiple large waves arrive in close succession, relaxation time shortens. The hull may still be under significant stress from the first impact when the second applies additional load. The third may strike at a moment of maximum dynamic stress. This is where size does not guarantee safety. Large ships have long natural periods of motion. Their pitch and roll cycles occur over longer intervals compared to smaller vessels. If incoming waves match or approach these natural periods, resonance can amplify motion. A long container ship encountering long-period storm swells may experience pronounced pitching. If 3 high crests arrive spaced in alignment with the ship's natural pitch frequency, motion amplitude increases. In addition to bending, there are local impact forces. When a steep or breaking wave strikes the bow, the forward structure absorbs significant energy. The flare of the bow is designed to deflect water downward, reducing deck impact. Yet in extreme conditions, water can rise high enough to strike superstructure and bridge windows. There have been documented cases where bridge windows were shattered by rogue waves or grouped extreme waves. The force required to break reinforced marine glass is substantial. That such events occur underscores the magnitude of impact pressures involved. Container ships face additional vulnerabilities. Containers are stacked high above deck. Each container is secured by twist locks and lashing rods, designed to withstand expected accelerations. If extreme rolling or pitching occurs, lateral forces increase dramatically. Once a few containers break free, they can compromise neighbouring stacks. The cascading effect can result in dozens or even hundreds of containers lost overboard. The structural integrity of the hull may remain intact while cargo loss still occurs. Yet in more severe cases, hull girder failure can happen. Though rare, there have been incidents where large vessels have broken apart in heavy seas. While causes often involve multiple factors such as corrosion, fatigue, or loading conditions, extreme wave bending moments are sometimes implicated. Tankers and bulk carriers carrying liquid or granular cargo face sloshing and shifting risks. In partially filled tanks, liquid motion can resonate with ship motion. If 3 large waves induce rapid pitch cycles, internal fluid movement can amplify stresses. Bulk cargo such as grain or ore can shift if holds are not perfectly filled and secured, altering stability mid-event. Stability itself is dynamic. A ship's ability to right itself after rolling depends on its metacentric height and weight distribution. After a severe roll induced by one wave, residual water on deck or shifted cargo can reduce stability margin. If 2 more waves follow quickly, the angle of heel may exceed safe limits before recovery is possible. There is also the matter of fatigue. Steel structures subjected to repeated cyclic stress accumulate microscopic damage over time. Most fatigue occurs over years, but extreme stress cycles delivered in rapid succession can propagate existing microcracks. A vessel already weakened by corrosion or prior damage is more susceptible to catastrophic failure under sudden extreme loading. Speed and heading influence vulnerability. A ship travelling at high speed into large waves increases relative impact velocity. Slowing down reduces some loads but may compromise manoeuvrability. Turning broadside to waves can increase roll amplitude. Captains must balance these factors under pressure. Modern ships rely on weather routing services that provide updated forecasts and suggest optimal paths to avoid the worst storms. Yet storms can intensify unexpectedly. Wave models may underestimate peak heights. A vessel already committed to a route may encounter conditions worse than predicted. Even the largest cruise ships, designed with passenger comfort in mind, are not immune. Though their hulls are strong, their large superstructures present significant surface area. Extreme waves striking high can cause local damage. While catastrophic structural failure is rare, the experience of encountering a massive wave remains intense. Size can even introduce disadvantages. A very long hull spanning multiple wave crests and troughs simultaneously experiences complex bending patterns. A smaller vessel might ride over a wave more simply. A longer ship can be positioned across varying phases of the wave field, increasing stress gradients along its length. wave height relative to ship length matters. When wavelength approaches ship length, bending effects are maximised. In severe storms, wavelengths can reach hundreds of metres, comparable to the length of large container ships. This alignment increases potential for significant hull stress. Another factor is unpredictability. Giant ships are engineered for expected extremes. But when wave amplification produces heights beyond statistical expectation, the safety margin narrows. The ocean does not provide warning labels indicating when a particular crest will exceed design assumptions. There is also human expectation. The sight of a massive ship can create a false sense of invulnerability. Crew members may underestimate risk, yet experienced mariners understand that scale offers resilience but not immunity. Documented maritime losses sometimes involve extreme weather where multiple factors converge: high winds, large waves, mechanical failure, cargo shift. In some cases, survivor accounts describe sequences of massive waves preceding loss. While not all such incidents are definitively linked to grouped extreme waves, the pattern is consistent with what physics allows. It is important not to dramatise unnecessarily. Millions of voyages occur safely each year. Modern ship design is robust. But robustness is not absolute protection. The ocean remains a dynamic environment capable of producing forces beyond average expectations. When 3 unusually large waves arrive in close succession, even a giant ship can be caught in a cycle of motion and stress that tests structural limits. The first destabilizes, the second compounds bending and acceleration, the third may strike at peak vulnerability. Understanding this vulnerability does not diminish engineering achievement. It highlights the challenge engineers face when designing structures for environments characterized by nonlinear extremes. And as we continue examining the interplay between steel hulls and amplified seas, it becomes necessary to look more closely at how structural limits are calculated, how hull geometry distributes stress, and how modern naval architecture attempts to anticipate forces that occasionally exceed prediction. When people imagine a large ocean-going vessel, they often picture something solid and unyielding. Steel plates several centimetres thick, internal frames spaced precisely along the length, bulkheads dividing compartments like the ribs of a massive mechanical creature. The word steel itself carries weight. It suggests strength, certainty, resistance. But steel is not indestructible, and a ship's hull, no matter how large, is not a rigid block. It is a carefully balanced structure designed to flex within limits. A modern cargo ship is essentially a floating beam. Its hull girder runs from bow to stern, distributing weight and buoyant support along its length. The deck acts as the upper flange of that beam. The keel and bottom plating act as the lower flange. Between them, longitudinal stiffeners and transverse frames hold everything in shape. Naval architects calculate loads using bending moment diagrams. They consider how buoyancy is distributed under different wave positions. In calm water, buoyancy roughly balances weight along the hull. In waves, buoyancy shifts. When a crest supports the midsection, upward force concentrates there. When troughs lie beneath the midsection, upward support decreases in the centre and increases near the ends. These alternating conditions produce sagging and hogging stresses. Engineers calculate the maximum expected values based on statistical wave models. They include safety margins. Steel's yield strength is known. Designers ensure that under predicted extreme loads, stress remains below critical thresholds. However, design assumptions depend on predicted extremes. Hull strength is not simply about plate thickness. It involves geometry. Curvature increases stiffness. Reinforcement placement matters. Openings such as hatch covers weaken continuous structural lines. Container ships, in particular, have large deck openings to accommodate cargo holds. These openings reduce torsional stiffness and make longitudinal strength even more critical. Steel itself has well-defined properties. It can withstand substantial tension and compression, but repeated loading can lead to fatigue. Microscopic cracks can develop at weld seams or stress concentration points. Over years of service, fatigue accumulates. Maintenance and inspection attempt to identify and repair these vulnerabilities before they grow. Now consider what happens during extreme wave encounters. When a very large wave supports only part of the hull, bending moments increase. The stress distribution changes rapidly as the ship moves relative to the wave. If 3 extreme waves arrive in succession, stress reversals occur quickly. The structure may experience tension, then compression, then tension again within short intervals. Dynamic loading adds complexity. The hull does not simply adopt a static bending shape, it vibrates. Impact from a steep or breaking wave introduces localized forces. Slamming can occur when the bow lifts clear of the water and then drops heavily into the next trough. The force of re-entry generates high local pressure on the forward bottom plating. Slamming loads can exceed hydrostatic pressures significantly. Naval architects account for slamming in design, reinforcing forward sections accordingly. Yet in unusually steep seas, slamming may occur repeatedly in quick succession. Steel behaves elastically within certain limits. Under elastic deformation, it returns to its original shape after load removal. If stress exceeds the elastic limit, plastic deformation begins. The steel permanently changes shape. In extreme cases, fracture can occur. Fracture risk depends not only on stress magnitude, but also on temperature and material quality. In cold environments, steel can become more brittle. Historically, brittle fracture contributed to structural failures in some vessels operating in frigid waters. Modern steel formulations and welding standards reduce this risk, but it remains a consideration. Another structural concern is torsion. When waves approach at an angle, one side of the hull may be supported by a crest while the other side is in a trough. This twisting introduces torsional stress. Large container ships with wide beams and open decks are particularly sensitive to torsional loading. In heavy quartering seas, the first large wave may induce significant twist. The second may reverse it. The third may arrive before torsional oscillations dampen. Rapid torsion cycles strain connections between structural members. Hatch covers represent another structural boundary. They must be watertight and strong enough to withstand green water loads when waves break over the deck. If hatch covers deform under extreme impact, water can enter cargo holds. Once water accumulates, additional weight alters trim and stability. Structural loads increase further. Bulk carriers have faced incidents where hatch cover failure allowed water ingress during storms. Combined with dynamic loading from waves, this can lead to progressive structural weakening. The interaction between cargo weight and hull stress is also important. A fully loaded ship distributes weight differently than an empty one. In heavy weather, ballast adjustments may be made to optimize stability. Improper loading can exacerbate bending stresses under wave action. Classification societies specify maximum allowable still water bending moments and wave-induced bending moments. Ships are monitored for loading conditions to ensure these limits are not exceeded. However, wave-induced loads fluctuate rapidly. While still water bending can be controlled through loading, wave loads depend on sea state. Hull monitoring systems now exist on some vessels. Strain gauges measure stress in real time. Data helps operators understand when loads approach critical values. In extreme storms, such monitoring can inform speed and heading adjustments. Despite all precautions, structural limits are finite. If wave height exceeds expected maximums, bending moments may surpass design criteria. Most ships have some reserve capacity beyond calculated limits, but that reserve is not infinite. Historical examples illustrate vulnerability. The sinking of the SS Edmund Fitzgerald in 1975 on Lake Superior remains a subject of investigation and debate. While exact causes are still discussed, some theories involve structural failure under severe wave conditions combined with water ingress. The lake's short, steep waves may have produced rapid stress cycling. In ocean contexts, large vessels have occasionally broken in two under extreme loading. Though rare, Such failures highlight the reality that steel structures subjected to unexpected loads can fracture. It is important to emphasize that modern naval architecture is highly advanced. Ships are not fragile. They are engineered to survive harsh conditions, but they are optimized for statistical environments, where nonlinear amplification produces rare extremes. Margins narrow. Structural response also depends on speed relative to waves. Slowing down can reduce slamming intensity, but may increase exposure time within a wave group. Increasing speed may reduce encounter frequency, but increase relative impact velocity. Captains must weigh these trade-offs in real time. Crew response affects structural stress as well. Securing loose equipment reduces secondary damage. Adjusting ballast can influence bending distribution. But once a sequence of extreme waves is underway, options become limited. It is not simply the height of waves that threaten structural limits. It is the combination of height, steepness, wavelength, relative to ship length, direction, and timing. 3 large waves arriving at just the wrong interval can synchronize with hull oscillations and stress reversals. Steel yields predictably under known conditions. The unpredictability lies in the ocean's ability to deliver load combinations beyond those known conditions. Even a structure built with conservative safety margins cannot be designed for every conceivable extreme without becoming impractically heavy and inefficient. Engineering always balances strength, weight, cost, and function. A ship must carry cargo efficiently. Excess reinforcement increases weight and reduces payload capacity. Design codes therefore aim for acceptable risk, rather than absolute invulnerability. This reality does not undermine confidence in modern ships. It clarifies the boundary between resilience and impossibility. The ocean's rarest alignments of energy can test even the strongest hull, and understanding these structural boundaries prepares us to examine the atmospheric forces that initiate the chain of events in the first place. Because before steel bends and hulls flex, wind and pressure begin shaping the waves that will eventually test them. Before a wave rises high enough to threaten steel, before interference amplifies crests or currents compress energy, there must first be wind. Not a casual breeze brushing the surface, but organised, sustained atmospheric motion shaped by pressure differences across vast regions. The architecture of wind determines the architecture of waves, and storm systems are the primary engineers. Wind exists because the atmosphere is unevenly heated. The equator receives more solar energy than the poles. Land heats and cools faster than water. Pressure differences develop. Air moves from high-pressure regions toward low-pressure regions. The rotation of the Earth deflects these flows through the Coriolis effect, shaping them into organised systems rather than straight-line currents. On a global scale, prevailing wind belts form. Trade winds dominate tropical regions. Westerlies influence mid-latitudes. Polar easterlies affect higher latitudes. These broad patterns provide the baseline motion of air over oceans, but it is within storm systems that wind becomes intense enough to build dangerous seas. A storm system is essentially a region of low atmospheric pressure surrounded by higher pressure. Air flows inward toward the low pressure centre. As it converges, it rises. Rising air cools, condenses moisture, and forms clouds and precipitation. The larger the pressure difference across a given distance, the stronger the resulting wind. Meteorologists refer to this pressure gradient as a key driver of wind speed. In mid-latitudes, extratropical cyclones dominate ocean storm activity. These systems form along boundaries between warm and cold air masses. The temperature contrast fuels instability. The low-pressure centre deepens as warm air rises and cold air descends. The tighter the pressure gradient, the faster the wind rotates around the centre. Over open oceans, extratropical cyclones can grow large and intense. The North Atlantic and North Pacific frequently experience powerful winter storms driven by strong temperature gradients between polar and subtropical air masses. These systems can span hundreds or even thousands of kilometres. Wind speed alone does not determine wave height. duration and fetch also matter. Fetch refers to the uninterrupted distance over which wind blows across water in a consistent direction. A strong wind blowing for a short time over a small area produces limited wave growth. A strong wind sustained for days across a vast stretch of ocean produces much larger waves. In large storm systems, fetch can extend for hundreds of kilometres. If wind direction remains steady, energy transfer continues without interruption. Waves grow both in height and wavelength. Longer waves carry more energy and travel faster, allowing them to outrun the storm that created them and propagate as swell. Tropical cyclones, known as hurricanes or typhoons depending on region, represent another powerful wind architecture. These storms form over warm tropical waters where sea surface temperatures exceed roughly 26 degrees Celsius. Warm water fuels convection, releasing latent heat that intensifies the storm's low-pressure core. Wind speeds around the eye wall can exceed 200 km per hour. The circular wind field of a tropical cyclone produces waves in multiple directions. On one side of the storm, wind and storm motion may align, increasing effective wind speed relative to the water surface. This can enhance wave growth dramatically. On the opposite side, opposing motion reduces relative wind speed, producing asymmetry in wave height distribution. The structure of wind within a storm is not uniform. Gusts and lulls occur. Squall lines can intensify local wind speeds temporarily. Embedded smaller-scale systems within a larger cyclone can create localized peaks in energy transfer. This variability introduces complexity into the resulting wave field. As waves grow under strong winds, they interact with the atmosphere above. The roughened sea surface increases drag on the air, modifying wind flow slightly. Spray from breaking crests becomes entrained in the air. This two-way interaction between air and sea influences how energy continues to transfer. Wind also determines wave direction. When winds shift during storm evolution, new wave systems develop on top of existing ones. For example, a storm may begin with southerly winds generating northward moving waves. As the storm center passes, winds may rotate and begin blowing from the opposite direction. New waves form travelling southward, intersecting with earlier waves. The result is a confused sea state with crossing wave patterns. In large extratropical cyclones, multiple frontal boundaries exist. Warm fronts and cold fronts move relative to the low-pressure center. Each front can generate its own wind pattern and associated wave field. As these fronts wrap around the cyclone, waves from different sectors interact. Pressure deepening plays a critical role. Rapid intensification, sometimes referred to as bomb cyclogenesis, occurs when a mid-latitude cyclone's central pressure drops rapidly over a short period. This steepens pressure gradients dramatically. Wind speeds increase, wave growth accelerates. Storm translation speed also matters. If a storm moves in the same direction as the waves it generates, waves can remain under strong wind influence longer, allowing them to grow larger. This phenomenon is known as dynamic fetch extension. The storm effectively travels with its wave field, feeding it energy continuously. Conversely, if a storm moves quickly away from its wave field, waves may not reach their maximum potential height. Timing between wind forcing and wave response shapes the resulting sea state. The architecture of wind determines not only wave height but wave period. Strong, sustained winds over long fetch produce long-period waves. Short-lived gusty winds produce shorter-period waves. Long-period waves travel faster and penetrate deeper into the water column. They also interact differently with ships compared to short, steep waves. Wind direction, relative to ocean currents, can further modify wave growth. In regions where strong surface currents exist, wind blowing against the current increases relative velocity between air and water, enhancing energy transfer. Wind blowing with the current reduces relative velocity slightly. Large-scale atmospheric patterns such as the North Atlantic Oscillation influence storm tracks and intensity over seasonal timescales. When pressure differences between Iceland and the Azores strengthen, westerly winds intensify across the North Atlantic, leading to more frequent and powerful storms. Seasonal variability therefore shapes the likelihood of encountering extreme seas. Wind shear within the atmosphere can affect storm organisation. In tropical cyclones, low vertical wind shear allows the storm to maintain a symmetric structure and intensify. High shear disrupts organisation, limiting maximum wind speeds and wave generation potential. Ocean temperature also feeds back into storm strength. Warmer sea surfaces provide more energy for tropical systems. In mid-latitudes, temperature contrast between ocean and air masses drive baroclinic instability. Changing climate patterns may influence these gradients, potentially altering storm intensity distributions over time. The energy transferred from wind to waves is gradual but cumulative. Wind does not instantly create large waves. It builds them step by step. Initial ripples form. As they grow, they increase surface roughness, which allows more efficient momentum transfer. Wave height increases until either wind weakens or wave growth reaches a limit imposed by gravity and braking. Fully developed seas occur when wind has blown long enough over sufficient fetch for waves to reach equilibrium with wind input. In such conditions, wave height and periods stabilize relative to wind speed. But if wind continues to strengthen or fetch extends further, waves grow beyond previous equilibrium states. Storm systems rarely remain steady. They intensify, weaken, change direction. Each change leaves its mark on the wave field. Old swells persist even after winds subside. New winds overlay fresh wave components. The ocean's surface becomes a layered record of atmospheric history. When multiple storm systems interact, complexity increases further. One storm's swell may propagate into the domain of another developing storm. Cross-interaction between wave systems can enhance interference patterns. Large waves generated far away can intersect with locally generated waves, creating regions of amplified motion. The spatial scale of storm systems is vast compared to ships. A cargo vessel may be 300 meters long. A mid-latitude cyclone can span 1,000 kilometers. Within that domain, wind speed varies by location relative to the center. The strongest winds often occur in specific quadrants. Ships positioned within those quadrants encounter the most severe wave growth. Forecasting storm-driven waves relies on numerical weather prediction models coupled with wave models. These systems ingest satellite data, buoy observations, and atmospheric measurements. They simulate wind fields and compute resulting wave spectra. Forecast accuracy has improved significantly over recent decades. However, models operate on grids with finite resolution. Small-scale gusts and micro-scale interactions may not be fully captured. While models predict general wave height distributions well, precise timing and local amplification events remain challenging to forecast with pinpoint accuracy. From a vessel's perspective, entering a storm means entering a complex, evolving field of wind-generated energy. The crew monitors barometric pressure, wind speed, and wave patterns. Decisions about course and speed are made in response to evolving conditions. Wind is the origin of wave energy in most open ocean extreme events. Without sustained wind forcing, large waves would dissipate. Gravity would flatten the surface over time. But as long as pressure gradients drive strong winds, energy continues to transfer into the sea. The architecture of wind, shaped by temperature gradients, planetary rotation, pressure systems, and seasonal patterns, ultimately determines the scale and structure of ocean waves. Storm systems act as energy engines. Their organization dictates whether waves grow modestly or reach heights capable of challenging even the strongest ships. And once wind has built those waves and released them across open water, the next layer of complexity emerges beneath the surface, where ocean currents flow invisibly and interact with the moving energy above in ways that can intensify or diminish what the wind has created. Wind may be the architect that builds waves, but beneath the visible surface there is another system quietly shaping their behaviour. Ocean currents move vast volumes of water across the globe. They are driven by wind, temperature differences, salinity gradients, and the rotation of the Earth. Most of the time, we do not see them directly. They do not rise like crests or crash like breakers. Yet when waves encounter these moving bodies of water, their shape and energy can change dramatically. To understand how, it helps to distinguish between waves and currents. A wave is primarily an oscillation of energy passing through water. The water particles move in circular orbits and largely return to their original positions. A current, by contrast, is the sustained movement of water in a particular direction. It carries mass. It transports heat, salt, and momentum. When a wave travels through still water, its speed depends on wavelength and gravity. In deep water, longer waves move faster than shorter ones. But when water itself is moving, the wave's behavior is altered. The wave's speed relative to the seabed becomes the sum of its speed relative to the water and the speed of the water itself. If a wave moves in the same direction as a current, its effective speed relative to the seabed increases. Its wavelength stretches slightly. The energy spreads over a longer horizontal distance. Wave height may decrease somewhat because energy density is reduced over the stretched wavelength. If, however, a wave travels against a current, the opposite happens. Its forward speed relative to the seabed decreases. Its wavelength shortens. The same energy becomes compressed into a smaller horizontal space. When wavelength decreases and energy remains roughly constant, amplitude increases. The wave grows steeper. This compression effect is one of the most important ways currents can intensify wave conditions. Imagine a storm-generated swell moving southward across the North Atlantic. Beneath it flows the Gulf Stream, a powerful northward-moving current. Where the swell encounters the opposing flow, wave speed relative to the seabed decreases. Wavelength shortens. Crests rise higher and become steeper. The sea surface appears more chaotic and aggressive than wind speed alone would suggest. This phenomenon has been documented in regions where strong currents meet storm waves. Off the coast of South Africa, the Agulhas current flows swiftly along the continental shelf. Storm waves travelling against it have produced some of the most extreme sea states recorded. Mariners in these waters have long reported unusually steep and powerful waves, even when wind conditions seem typical for a storm. The mathematics behind this interaction can be described through conservation of wave action. Wave energy flux must remain consistent unless additional energy is added or removed. When opposing current reduces wave group velocity, energy density increases. Height rises accordingly. Currents also influence wave breaking. As steepness increases due to wavelength shortening, waves approach the critical threshold for instability. Breaking becomes more likely. Breaking waves release concentrated energy and produce higher impact pressures on ships. Beyond large, well-known currents like the Gulf Stream, there are countless smaller-scale currents throughout the ocean. Tidal currents near coastlines can be strong and highly variable. When storm waves encounter ebbing tides moving against them, local amplification can occur. This effect is familiar to mariners navigating river mouths and narrow straits, where waves steepen dramatically under opposing flow. Even relatively modest currents can have measurable effects when interacting with large swells. A current of 2 or 3 knots may seem slow compared to wave speeds of 10 or 15 meters per second. But because wave speed depends on wavelength, and because opposing flow alters wavelength significantly, even small current velocities can produce noticeable changes in steepness. Currents are not uniform with depth. Surface currents may differ from deeper flows. Wind-driven surface layers can move in one direction, while deeper thermohaline currents move in another. Waves primarily interact with the upper layer of water where particle motion is strongest. Yet variations in current speed with depth can influence stability and energy transfer. Ocean fronts, where water masses of different temperature or salinity meet, can also create sharp current gradients. These fronts may not be visible from the deck of a ship. But when waves cross such boundaries, changes in current speed can alter wave shape suddenly. A ship entering a frontal zone may experience abrupt changes in sea state. Eddies, which are rotating bodies of water ranging from kilometres to hundreds of kilometres in diameter, introduce further complexity. When waves pass over eddies, current direction and speed vary spatially. In some regions of the eddy, waves may be amplified, in others, reduced. The sea surface can appear irregular and unpredictable. Bathymetry interacts with currents as well. When currents flow over underwater ridges or through narrow channels, their speed can increase. If waves encounter these accelerated currents, amplification intensifies locally. Regions of shallow banks or seamounts can therefore become hotspots for steep, dangerous waves during storms. The combined effect of wind-generated waves and current-induced modification creates a layered dynamic. Wind may build waves to a certain height. Currents then reshape those waves, compressing or stretching them. Interference between wave components continues simultaneously. From the perspective of a ship, current influence may not be obvious at first. Wind speed may remain steady, wave period may appear consistent, yet the steepness of the approaching waves can increase noticeably as the vessel crosses into a region of opposing flow. The angle of wave faces becomes sharper, impacts become more abrupt. In extreme cases, this interaction can contribute to rogue wave formation. A wave group amplified by nonlinear interference may become further intensified when entering an opposing current. The crest height can increase beyond what either mechanism alone would produce. Timing again becomes critical. If three amplified waves within a group intersect a current zone simultaneously, their heights may exceed expectations dramatically. A vessel encountering such a sequence experiences compounded forces. Modern oceanographic models incorporate current fields into wave predictions. Coupled wave current models simulate how energy propagates across dynamic water masses. Satellite observations track surface current patterns, yet real-time local variations can still surprise. For navigators, knowledge of current systems is essential. Weather routing services account for major currents when advising on storm avoidance. Mariners crossing the Gulf Stream during winter storms are well aware of the increased risk of steep, hazardous seas. Currents also influence ship motion directly. A vessel moving through a strong current must adjust heading to maintain course. Combined with wave impact, this adjustment can alter the angle at which waves strike the hull. An unfavourable angle may increase rolling or pitching. There is a subtlety here worth noting. Waves are visible and dramatic. Currents are invisible and constant. Because they cannot be seen directly from above, their influence may be underestimated, yet they act as a hidden architecture beneath the visible storm, shaping how energy organises at the surface. The global conveyor belt of ocean circulation, driven by temperature and salinity differences, moves water masses across basins over years. Surface wind-driven currents move more quickly, shaping regional sea states daily. Both systems interact with waves in different ways. In equatorial regions, trade winds drive westward surface currents. In higher latitudes, westerlies drive eastward currents. Where these systems converge or diverge, complex patterns emerge. Wave behaviour reflects these underlying flows. The ocean is therefore not a passive recipient of atmospheric forcing. It is an active participant. Wind builds waves. Currents reshape them. Interference amplifies them. Steepness triggers braking. Each layer contributes to the final form a crest takes when it rises ahead of a ship. When considering the three sisters or rogue wave sequences, currents can act as amplifiers. They do not create energy from nothing. They reorganize it spatially. They compress wavelength. They increase steepness. They push the system closer to thresholds. And as measurement technology improves, scientists continue to refine their understanding of these interactions, using satellites and offshore instruments to observe the ocean's surface and subsurface simultaneously, seeking patterns that reveal where and when amplification may occur. For most of human history, knowledge of the open ocean depended on what could be seen from a deck. A captain judged wave height by eye. A sailor estimated wind strength by the strain in the rigging. Even in the early scientific era, measurements were local. A buoy recorded what passed beneath it. A ship logged what it experienced along its path. The ocean beyond remained largely unmeasured. That changed when we lifted our instruments into orbit. Modern ocean observation relies heavily on satellites equipped with radar altimeters. These instruments do not see waves in the way a human sees them. They send microwave pulses down toward the sea surface and measure the time it takes for the signal to return. Because the speed of light is known, the distance between satellite and surface can be calculated with remarkable precision. As the radar pulse reflects off wave crests and troughs, the returned signal carries information about surface roughness. By analysing the shape and timing of the returned echo, scientists can estimate significant wave height over broad swathes of ocean. Each satellite pass produces a narrow track of measurements, but with multiple satellites operating simultaneously, global coverage becomes possible. This shift from local observation to global monitoring has transformed our understanding of extreme waves. Where once rogue waves were dismissed as anecdotal, satellite altimetry has confirmed their presence across many ocean basins. By scanning millions of square kilometres, satellites detect rare peaks that might never intersect a buoy or a ship. However, satellites have limitations. They pass over a given location only periodically. A rogue wave lasting seconds may occur between passes. Spatial resolution, though improving, still averages wave height over areas of several kilometres. Fine-scale structures may not be fully resolved. Even so, the statistical record built from years of satellite data has revealed that extreme waves occur more frequently than earlier linear models predicted. In addition to altimeters, synthetic aperture radar systems provide detailed images of the sea surface. These systems can capture wave patterns over wide areas, revealing directional spreading and interference structures. By examining wave spectra derived from radar images, researchers can infer where energy concentration may be occurring. Beyond satellites, a network of moored and drifting buoys provides continuous surface-level measurements. These buoys record wave height, period and direction using accelerometers and tilt sensors. Some are anchored in place, others drift with currents, transmitting data via satellite to forecasting centres. Offshore platforms, oil rigs and research stations contribute additional data. The famous Draupner platform measurement of 1995 came from such a fixed installation. These structures provide stable platforms for instruments capable of high-frequency recording. Unlike satellites, they can capture rapid events with fine temporal resolution. Ships themselves increasingly act as observation platforms. Modern vessels may carry wave radar systems mounted on the bridge. These systems scan the surrounding sea surface and estimate wave height and direction in real time. Some research initiatives encourage merchant ships to share anonymized wave data to enhance forecasting accuracy. Numerical models form the third pillar of modern ocean observation. Weather prediction models simulate atmospheric pressure fields and wind speeds. These outputs feed into wave models, which calculate how wind energy transfers into waves and how waves propagate across basins. The models incorporate current data and bathymetry to refine predictions. Wave models divide the ocean into grid cells. Within each cell, they compute a wave energy spectrum across frequencies and directions. They simulate how energy moves between cells and how nonlinear interactions modify amplitude distribution. These models can forecast significant wave heights several days in advance with reasonable accuracy. Yet despite these advances, prediction of specific extreme events remains difficult. Models predict statistical conditions, not individual crests. They can estimate that a region will experience high waves, but they cannot specify the precise timing and location of a rogue wave or a three-wave amplification sequence. Part of the challenge lies in resolution. The ocean surface evolves rapidly. Wave groups form and dissipate over scales of hundreds of meters and seconds to minutes. Global models often operate at grid resolutions of tens of kilometers and time steps of hours. Fine-scale, non-linear processes occur below these scales. Researchers are developing higher-resolution regional models to address this gap. By focusing computational power on storm zones, these models attempt to simulate wave group evolution more precisely. They incorporate detailed current maps and wind gust variability. Machine learning techniques are also entering the field. By training algorithms on large datasets of wave measurements, scientists hope to identify patterns that precede extreme amplification. For example, certain spectral shapes may correlate with increased probability of rogue wave formation. Real-time analysis of wave spectra from shipborne radar could potentially provide short-term warnings. However, the time window for action remains narrow. Even if an algorithm identifies growing modulation within a wave field, the interval between detection and crest formation may be seconds to a few minutes. For large ships with limited maneuverability, options are constrained. Ocean observation also extends below the surface. Acoustic Doppler current profilers measure subsurface current speeds at various depths. Understanding vertical current structure helps refine models of wave current interaction. When strong shear exists in the upper water column, wave behavior can change in subtle ways. Satellites measure sea surface temperature as well. Warm water fuels tropical cyclones, and temperature gradients influence mid-latitude storm development. By tracking temperature anomalies, forecasters can anticipate regions where storm intensification and wave growth are more likely. The integration of all these data sources creates a layered monitoring system. Satellites provide global perspective. Buoys and platforms supply local detail. Models integrate and forecast. Ships contribute situational awareness. For mariners, access to this information has improved dramatically. Bridge systems display updated wave forecasts. Routing software suggests paths that minimize exposure to extreme conditions. Captains can receive near real-time updates about storm intensification, yet technology does not eliminate uncertainty. Forecasts rely on initial conditions. Small errors in atmospheric models can propagate into wave predictions. Sudden storm deepening or unexpected current interactions can produce conditions exceeding forecasts. It is worth noting that observation technology has also corrected misconceptions. For years, many believed rogue waves were exceedingly rare, perhaps occurring only once in decades. Satellite records indicate they occur far more frequently across global oceans. Most do not intersect ships. They rise and fall unnoticed, but their existence is not mythical. Similarly, grouped extreme waves consistent with the Three Sisters pattern have been observed in instrument data. Wave records sometimes show clusters of high peaks within short intervals, validating long-standing sailor reports. Modern ocean observation does not render the sea predictable in every detail. It reduces uncertainty. It reveals patterns invisible to earlier generations. It quantifies risk more accurately. There is a quiet irony in this. Satellites orbit hundreds of kilometers above Earth, measuring the subtle rise and fall of water far below. A crest that lasts seconds leaves a measurable signature in radar echoes. From space, the ocean surface becomes a data field, yet even with eyes in orbit, the ocean retains complexity. Nonlinear interactions occur at scales difficult to resolve. Phase alignment between waves depends on precise timing. Currents shift subtly. Gusts inject energy irregularly. Technology has illuminated much of what once lay hidden. It has confirmed that extreme waves and clustered amplification are real phenomena grounded in physics. It has improved our ability to forecast general storm severity. But it has not removed the ocean's capacity to produce rare alignments of energy that challenge even the strongest structures. And as we consider how uncommon yet inevitable these events are, the question naturally turns toward how rare the Three Sisters truly are, and what statistical frameworks say about their likelihood. If the ocean is capable of producing rogue waves and amplified clusters of extreme crests, a natural question follows. Why are events like the Three Sisters not happening constantly? Storms occur every day somewhere on Earth. Waves overlap continuously. Currents flow without pause. And yet sequences of 3 unusually large waves striking in rapid succession remain rare enough to stand out in maritime memory. The answer lies in probability, alignment, and the delicate balance required for amplification to persist across multiple cycles. To begin with, most waves in a storm do not exceed the significant wave height by a dramatic margin. Even in severe weather, wave heights follow a statistical distribution. The majority cluster around an average. A smaller fraction rise above it. A very small fraction rise significantly above it. In simple linear models, wave heights approximate a Gaussian distribution. Under that assumption, extremely large waves would be extraordinarily unlikely. However, nonlinear effects introduce heavy tails into the distribution, increasing the probability of outliers. Even so, the probability remains low relative to total wave count. Now consider what is required for the Three Sisters pattern to occur. One unusually large wave is rare but plausible. For 3 to occur consecutively within the same wave group, several conditions must align. First, the wave spectrum must be narrow enough to allow sustained modulation. If the spectrum is too broad, phase relationships shift quickly and alignment dissipates after one crest. A narrow spectral band increases the chance that the envelope peak persists across several cycles. Second, nonlinear interactions must be strong enough to amplify crests significantly. This typically requires high wave steepness and sufficient energy density within the storm system. Not all storms generate conditions intense enough for strong modulation instability. Third, wave direction must be relatively coherent. If waves approach from many different angles, interference patterns become spatially scattered. Coherence in direction enhances the likelihood that large crests align, not only in time, but also across the width of the vessel encountering them. Fourth, current conditions can either enhance or diminish amplification. An opposing current can increase steepness and raise crest heights. Without such current interaction, wave amplification may remain below extreme thresholds. Finally, timing relative to a vessel's position determines whether the sequence becomes a threat. Even if a wave group contains 3 high crests, they must intersect the vessel at a moment when the ship's orientation and motion amplify stress. The ocean does not target ships. Ships simply happen to cross certain locations at certain times. These layers of probability multiply. The likelihood of one large crest occurring within a storm is measurable. The likelihood of 3 within one envelope peak is smaller. The likelihood that a ship encounters them at peak alignment is smaller still. This multiplicative nature of probability explains rarity. There is also the matter of spatial scale. The ocean's surface covers over 360 million square kilometres. Storm systems may span thousands of kilometres. Within these vast regions, small zones of peak amplification form and dissipate constantly. Most go unobserved because no vessel is present. Imagine a storm field producing millions of waves over its lifetime. Among them, a handful of wave groups may contain extreme amplification. Among those, only a subset may produce 3 consecutive high crests. Among those, only a few may intersect a vessel's path. From a global perspective, such events may occur regularly somewhere. From the perspective of an individual ship, they remain rare. Another factor is energy dissipation. Breaking waves release energy rapidly. When a crest becomes too steep, it collapses and dissipates part of its energy into turbulence and spray. This process limits how long extreme amplification can persist. Sustaining 3 consecutive high crests requires a delicate balance. Strong enough nonlinear interaction to amplify, but not so strong that breaking immediately dissipates the energy after the first crest. Storm evolution further limits duration. Pressure gradients shift, wind speed fluctuates, direction changes. The spectral shape of the wave field evolves constantly. The envelope peak responsible for amplification is transient. It may exist for minutes before dispersing. Mathematically, The Benjamin Fair instability predicts growth and decay cycles within wave trains. The envelope grows, peaks, and then diminishes. The peak region may encompass several wave cycles. Outside that region, amplitude returns to typical levels. The width of this envelope peak determines how many elevated crests occur consecutively. In many cases, the peak is narrow, allowing only one or two significant crests. In fewer cases, it spans 3 or more. Wave steepness also plays a limiting role. As amplitude increases, steepness approaches instability thresholds. Braking occurs, dissipating energy. The more intense the amplification, the shorter its lifespan. This natural damping mechanism prevents runaway growth. There is a comparison here with other nonlinear systems. In financial markets, extreme spikes occur rarely but inevitably over long timescales. In seismic systems, large earthquakes are rare relative to minor tremors. In each case, heavy tail distributions describe the probability of extreme events. They are unlikely in the short term but certain over long enough observation. Ocean wave statistics follow similar patterns. Extreme clusters are improbable in any given hour at any given location, but across global oceans and over years they will occur. It's important to distinguish between statistical rarity and impossibility. The Three Sisters phenomenon does not require extraordinary forces beyond known physics. It requires ordinary forces aligning in uncommon ways. Seasonal patterns influence probability as well. Winter months in mid-latitudes produce more intense extratropical cyclones. The North Atlantic, North Pacific and Southern Ocean experience higher wave energy during these periods. The likelihood of extreme group formation increases accordingly. Geographic features concentrate risk. Regions where strong currents meet storm tracks, such as the Agulhas Current, Gulf Stream, and Kuroshio Current, show higher frequencies of steep, amplified waves. In these areas, the probability of clustered extreme waves is elevated compared to calmer regions. Ship traffic density also affects perception of rarity. Major shipping lanes cross certain storm-prone areas frequently. If an extreme sequence occurs in a heavily trafficked region, it is more likely to be reported. In remote ocean sectors, similar events may pass without documentation. Technological improvements have changed our understanding of frequency. As satellite records accumulate, it becomes clear that extreme waves are not singular anomalies occurring once in decades. They occur more often than early linear models predicted. Still, 3 consecutive extreme crests within a short time window remain statistically uncommon. One might think of the Three Sisters as the product of overlapping filters. A storm must be strong enough. The wave spectrum must be narrow enough. Directional coherence must be sufficient. Nonlinear amplification must peak. Currents may need to align. A vessel must intersect at the right moment. Each filter reduces probability. Yet over long timescales, the filters occasionally align. The rarity contributes to the phenomenon's power in maritime memory. Events that occur infrequently but with high consequence leave strong impressions. Sailors remember the time when 3 towering waves struck in rapid succession. They do not recall the thousands of ordinary waves encountered daily. From a design standpoint, engineers must decide how much weight to give to rare extremes. Designing for the absolute worst conceivable alignment would require excessive reinforcement, increasing cost and reducing efficiency. Instead, ships are designed for statistically significant extremes with safety margins. Rare outliers remain part of residual risk. Understanding rarity does not eliminate danger. It clarifies expectations. Mariners may sail for years without encountering such sequences. That does not mean they are immune. As we examine how rare events fit into the broader rhythm of the ocean, it becomes useful to consider timing more deeply, not just statistical probability over years, but the subtle temporal patterns within wave groups that determine when energy peaks and how those peaks interact with motion on the surface. When sailors speak about dangerous seas, they often describe height first. The size of the wave, the steepness of the face, the force of impact. But beneath height lies something more subtle and just as important. Timing. The ocean does not move randomly, it moves in rhythms. Not visible rhythms like the ticking of a clock, but oscillations governed by gravity, inertia, and dispersion. Every wave carries a period. Every vessel carries its own natural motion period. When those periods interact, outcomes change dramatically. A wave period is the time between successive crests passing a fixed point. In moderate seas, this might be 6 to 8 seconds. In large storm swells, periods may extend to 15 or even 20 seconds. Longer periods mean longer wavelengths and faster propagation. Ships also have motion periods. A large container ship may have a natural pitch period of 10 to 15 seconds, depending on its length and loading condition. Roll period depends on beam width and stability characteristics and might fall within similar ranges. When incoming waves match or approach a vessel's natural motion period, resonance becomes possible. The first wave induces motion. The ship begins to pitch or roll. If the next wave arrives at the precise moment when the vessel's motion aligns with the new forcing, amplitude increases rather than dampens. This is not unlike pushing someone on a swing. Push at random times and motion remains small. Push at the right interval, matching the swing's natural frequency, and motion grows. In heavy seas, if 3 large waves arrive spaced at intervals matching the ship's pitch period, each successive crest reinforces motion. The first lifts the bow. The second arrives as the bow descends, adding energy. The third arrives at peak oscillation. The structural loads during the third encounter can exceed those of the first 2 combined. Timing within the wave group itself is also critical. As discussed earlier, wave groups form due to modulation. The envelope of a group may contain several elevated crests. The spacing between these crests is not random. It reflects the dominant period of the underlying wave components. If the envelope peak spans 3 wave cycles, the crests are separated by consistent intervals. The persistence of high amplitude across those intervals allows the 3 sisters pattern to emerge. Dispersion adds another temporal layer. Longer waves travel faster than shorter ones. Over time, wave trains reorganize. Faster components move ahead. Slower components lag. This reshaping alters the phase relationships that determine constructive interference. Sometimes, dispersion sharpens group peaks temporarily before spreading them out. During this window, amplitude concentration increases. Afterward, the group disperses and heights normalize. Storm motion relative to waves influences timing as well. If a storm moves in the same direction as its waves at similar speed, wave growth persists longer. The storm effectively stays with the wave group, maintaining energy input. If storm speed matches group velocity closely, the envelope peak can strengthen over multiple cycles. There is also the hidden rhythm of atmospheric pressure fluctuations. Rapid drops in pressure during storm deepening can subtly alter sea level beneath the storm center. While this effect is small relative to wave height, it influences baseline water elevation. Combined with wave crests, these subtle shifts can alter impact geometry. On shorter timescales, gust patterns within the wind field inject energy unevenly. A gust arriving at the moment of crest formation can increase amplitude slightly. If gust timing aligns with existing modulation peaks, amplification intensifies. Currents introduce timing effects as well. When waves move into opposing flow, group velocity decreases. This means the envelope peak lingers longer over a given location. If a vessel is within that zone, it may encounter multiple high crests within a shorter spatial region than expected. The interplay between group velocity and phase velocity is central here. Individual crests move at phase velocity. The energy envelope moves at group velocity. In deep water, group velocity is half of phase velocity. This means that while individual crests appear to pass quickly, The region of highest energy moves more slowly. The envelope lingers. For a ship entering such an envelope, the experience can feel compressed. High waves arrive one after another before the sea returns to more moderate levels. Another aspect of timing lies in structural response. When steel flexes under load, it does not respond instantaneously and then stop. There is dynamic vibration. The hull oscillates slightly even after the wave passes. If another load arrives during this oscillation, stresses superimpose. Damping mechanisms within the structure and surrounding water reduce motion gradually. But if loads arrive before damping completes, oscillation amplitude increases. Even the human nervous system has a timing threshold. After a severe wave impact, crew members react, secure equipment, adjust stance. If another wave arrives too quickly, response is incomplete. The third wave may strike before corrective action is finished. Ocean timing operates across scales. Tidal cycles shift currents over hours. Storm intensification unfolds over days. Wave groups evolve over minutes. Individual crest impacts occur over seconds. The Three Sisters phenomenon exists within the shortest of these timescales, where seconds determine outcome. Statistically, the probability of three extreme crests occurring consecutively depends on the persistence of high envelope amplitude across multiple periods. This persistence is sensitive to small changes in spectral width and phase alignment. Slight variation in frequency distribution can shorten or lengthen the envelope peak. Think of the wave spectrum as a musical chord. If frequencies are tightly grouped, the resulting beat pattern is slow and pronounced. If frequencies are spread widely, the beat pattern is rapid and irregular. The ocean's hidden rhythm depends on this spectral structure. When spectral bandwidth narrows during certain storm conditions, beat patterns lengthen. Envelope peaks span multiple cycles. That is when the rhythm allows three significant crests to rise in succession. The rarity of this alignment reinforces how dependent it is on precise timing. Not only must waves align spatially, they must remain aligned temporally across successive oscillations. It is easy to focus on height because it is visible. Timing is invisible, yet timing determines whether amplification persists or dissipates, whether resonance builds or fades, whether stress accumulates or relaxes. In many voyages, ships encounter large waves that are separated by enough time to recover fully between impacts. The hidden rhythm remains forgiving. But when rhythm tightens, when crests follow one another in measured intervals matching vessel motion, recovery time shrinks. Time in the ocean is layered. The long rhythm of tides, the medium rhythm of storms, the short rhythm of wave groups. And within those short rhythms, moments where alignment across energy, motion and structure coincide. Understanding this temporal dimension clarifies why extreme sequences feel sudden yet structured. They are not chaotic bursts without pattern. They are the product of overlapping oscillations reaching peak alignment at just the wrong interval. And once timing aligns across waves, currents and structural motion, the phenomenon transitions from theoretical possibility to lived experience, which is why examining real encounters at sea reveals how these rhythms have manifested in documented events. There is a difference between knowing something is possible and seeing it rise in front of you. A crew member standing on the bridge of a large vessel during heavy weather is trained to read instruments, not emotions. Radar returns, wind speed indicators, wave radar overlays, hull stress monitors. Numbers matter, procedures matter, calm communication matters. But when an unusually steep wall of water begins to rise ahead of the bow, numbers momentarily become secondary. The human brain evolved in landscapes defined by solid ground. Mountains do not move, cliffs do not surge forward. The ocean challenges this instinct. A wave that towers above the horizon line appears, for a moment, like terrain that has broken free from the earth and begun advancing. Even experienced sailors describe extreme waves in physical terms: a wall, a ridge, a mountain. These metaphors are not poetic exaggerations. They reflect the brain's attempt to categorize scale and threat using familiar reference points. When a large vessel encounters heavy seas regularly, the crew adapts psychologically. Routine forms, the motion becomes predictable, the mind anticipates the rhythm. When waves behave within expected parameters, stress remains manageable. The Three Sisters pattern disrupts that predictability. The first unusually large wave often triggers surprise more than fear. The vessel climbs higher than expected. The bow may shudder under impact. Crew members tighten their grip on railings. But if the ship stabilizes afterward, confidence returns briefly. When the second wave rises before recovery is complete, perception shifts. Surprise becomes alertness. The brain recognizes pattern repetition. The nervous system increases adrenaline output. Heart rate rises. Focus narrows. By the time the third wave approaches, the body is already in heightened physiological response. Muscles tense. Vision sharpens. Auditory perception filters out irrelevant sounds. The brain prepares for impact. Psychology under extreme marine conditions is influenced by scale. On a small vessel, proximity to the water intensifies fear. On a large vessel, height above the surface provides some psychological buffer. Yet when waves reach bridge level or crash over deck structures, that buffer collapses. Crew training emphasizes composure. Maritime operations rely on calm decision-making. Panic spreads quickly in confined environments. Leaders on the bridge maintain measured tone even during severe impacts. This steadiness influences crew response below deck. However, psychological stress is cumulative. The first wave startles. The second confirms severity. The third tests emotional resilience. When extreme events occur in rapid succession, recovery time between stress spikes is limited. The unpredictability of rogue or grouped extreme waves amplifies stress. Humans cope better with known intervals. If waves follow steady rhythm, anticipation becomes possible. When an unusually steep crest appears outside expected pattern, uncertainty increases. There is also a sensory dimension. Sound plays a major role. The deep roar of wind, the sharp crack of water striking steel, the vibration transmitted through the hull. In extreme impacts, these sounds intensify abruptly. Sudden loud noise triggers instinctive stress response. Visual perception shifts as well. In heavy seas at night, visibility may be limited to what deck lights illuminate. A towering wave emerging from darkness can feel sudden, even if radar indicated heavy seas ahead. Daylight provides more visual warning but does not reduce scale. Experience modifies psychological response. Veteran mariners who have encountered severe storms before may remain outwardly calm during extreme wave sequences. Their memory contains reference points. They know that survival is possible. Newer crew members may react differently. Without prior experience, scale can overwhelm. Training drills attempt to prepare crews for heavy weather scenarios, but simulation cannot fully replicate the sensory impact of a real extreme wave. There is a cognitive element related to control. Humans tolerate risk better when they feel capable of influencing outcome. In extreme seas, control narrows. Course adjustments may help, but wave alignment cannot be commanded. The realization that certain forces are beyond manipulation increases stress. Yet there is also a counterbalancing effect. Structured training reduces uncertainty. Knowing procedures for securing equipment, adjusting speed, and communicating reduces cognitive overload. Clear roles within the crew maintain functional order. On larger vessels, the bridge team operates collaboratively. One officer monitors radar, another tracks heading and speed. The captain oversees decisions. Distributed responsibility reduces individual cognitive burden. Still, the physical presence of a massive wave overrides abstract understanding. A crest 30 meters high, even when anticipated intellectually, produces visceral reaction. The brain registers vertical displacement and relative motion instantly. The sensation of climbing a steep wave is unique. The bow rises. The horizon tilts downward. gravity shifts relative to the deck, objects not secured slide. As the vessel crests and begins descending, acceleration changes abruptly. In extreme cases, there is a momentary sense of weightlessness. Repeated rapidly, these sensations strain psychological endurance. After two severe impacts, anticipation of a third creates heightened vigilance. The body remains in fight or flight mode longer than usual. Interestingly, some mariners report a paradoxical calm during the most intense moments. When threat is immediate and clear, focus sharpens. There is no room for distraction. Every action is deliberate. The mind narrows to essential tasks. After the sequence passes, delayed stress often surfaces. Hands may tremble. Breathing normalizes slowly. Crew members exchange brief remarks acknowledging what just occurred. The human system recalibrates. Long-term psychological effects from single extreme wave encounters are uncommon but not non-existent. Repeated exposure to severe storms over years can produce chronic stress in some individuals. Maritime professions incorporate mental resilience training to mitigate this. There is also collective psychology within the maritime community. Stories of extreme waves circulate. They reinforce respect for the sea. They shape caution without necessarily inducing fear. Knowledge that even large ships can be challenged fosters vigilance. From a design perspective, understanding crew psychology matters. Bridge windows are reinforced not only for structural reasons but also to maintain sense of security. Clear communication systems reduce confusion during high-stress moments. Ergonomic bridge layouts minimize disorientation during heavy roll. The perception of scale plays a central role in how the Three Sisters phenomenon is remembered. Three massive waves in succession create a narrative arc. The first introduces danger, the second escalates it, the third resolves it. Human memory organizes experience in sequences. Even though physics explains the mechanism, the lived experience remains emotional. Facing a moving mountain of water activates instincts older than engineering. The ocean does not intend intimidation. It follows energy gradients and fluid dynamics. But the human mind interprets vertical mass moving toward it as threat. This interpretation shapes reaction, decision-making, and memory. And when such encounters are documented in logs, reports, and investigations, they become part of maritime history. Which is why examining real cases where ships have faced extreme clustered waves reveals how psychology, physics, and structural limits intersect in practice. There is a moment that follows extreme impact at sea that does not appear in wave models or structural calculations. It is the silence, not the absence of wind, not the absence of water. The engines still hum, the storm still moves. But immediately after a massive wave strikes, there is often a short pause in human sound. No one speaks for a second or two. The ship groans. Loose items settle. Then voices return. Survivor accounts from severe ocean encounters often focus on that interval. When crews describe meeting three unusually large waves in succession, they rarely begin with statistics. They begin with what they felt. The first wave rising higher than expected, the bow climbing at an angle that strained perspective, the impact shaking fittings that had remained steady through hours of heavy weather. In many accounts, the first wave produces disbelief more than fear. Experienced sailors know storms can intensify temporarily. They brace, they check instruments, they confirm heading. There is tension, but it remains contained. Then the second wave appears sooner than expected. Several survivors of North Atlantic storms have described how the second crest seemed to rise before the vessel fully recovered from the first. One officer recalled watching green water sweep across the forward deck, while the stern was still descending from the previous climb. The rhythm felt compressed. Orders were given quickly. Engine speed adjusted slightly. Crew secured interior doors. By the time the third wave approached, anticipation had replaced surprise. Those on deck or bridge described watching its face build, darker and steeper than the rest of the sea. The third impact often felt heavier not only because of physical force, but because the structure was already in motion. After such a sequence, reports consistently mention assessment, silence, then rapid checking, hull stress monitors reviewed, crew members accounted for, cargo lashings inspected where possible. The first priority is always confirmation that the vessel remains structurally sound. There are documented cases where ships survived extreme wave clusters but sustained damage. Bridge windows shattered, deck equipment torn loose, containers lost overboard. In each case, crew narratives emphasize the rapid succession of impacts rather than a single isolated crest. One mariner who survived a severe South Atlantic storm described seeing what he believed was a rogue wave followed by two nearly equal crests. The first broke against the bow and sent spray as high as the bridge. The second struck while water was still draining from the deck. The third arrived moments later, causing the vessel to roll more sharply than at any previous point in the storm. Afterward, there was a moment where everyone simply listened, to engines, to hull sounds, to alarms, waiting to confirm nothing catastrophic had occurred. Another account from a North Pacific container ship described a night encounter where radar had indicated heavy seas, but not extraordinary peaks. The first large wave slammed against the starboard bow, throwing the vessel off planned heading briefly. The second followed within seconds, increasing roll angle. The third caused cargo sensors to register abnormal acceleration. In the quiet afterward, crew members reported a sense of disbelief at how quickly conditions had escalated. Not all encounters end safely. Investigations into certain maritime losses reference survivor statements describing sequences of unusually large waves prior to abandonment. In some cases, surviving crew from lifeboats have reported that the vessel experienced multiple massive impacts in rapid succession before structural failure or catastrophic flooding. It is important to approach such accounts carefully. Memory under stress can distort timing and scale. Yet when multiple independent testimonies from different vessels and regions describe similar patterns, the consistency becomes significant. Silence after impact often carries meaning. It is the moment when the human system recalibrates. Adrenaline peaks during the approach. Impact releases it. The immediate quiet allows assessment. Engineers reviewing incident reports pay attention to descriptions of timing. How many seconds separated crests? What was the approximate period? Did the vessel change heading between waves? Survivor testimony, though subjective, provides clues that instruments alone may not capture. There is also the contrast between sound and vibration. A massive wave impact produces a deep, resonant thud through steel. The entire hull can tremble briefly. After 3 such impacts, crews often report heightened sensitivity to any unusual noise. Even routine creaks may be interpreted as warning until inspected. Some accounts emphasize the visual aspect. During daylight encounters, crew members describe watching a wall of water block out sections of sky. During night encounters, they speak of darkness suddenly filled with white spray, illuminated by deck lights. In both cases, the third wave is remembered most vividly. The memory structure follows a pattern: first shock, escalation, climax, aftermath. Survivors frequently mention checking for water ingress immediately afterward. In heavy seas, even intact vessels may take on spray and minor leakage. After extreme waves, the concern intensifies. Pumps are monitored, bilges inspected, communication between compartments confirmed. In a few recorded cases, wave clusters have disabled equipment temporarily. Electrical systems exposed to heavy spray may short momentarily. Communication systems can fail if antennas are damaged. Survivors describe brief confusion during such interruptions. Psychologically, the silence also reflects collective processing. Crews look at one another to confirm shared experience. Nods are exchanged. Brief remarks acknowledge scale. Then routine resumes. There are instances where vessels lost containers or suffered deck damage during such sequences but continued voyage. Logs record the time and estimated position. Later inspection in port confirmed structural integrity remained within tolerance. In these cases, the Three Sisters become a story of survival rather than loss. Maritime culture values understatement. Survivor accounts often avoid dramatic language. Statements such as "encountered 3 unusually heavy seas in succession" may conceal events that felt extraordinary in the moment. The restraint reflects professionalism. In contrast, passengers on cruise vessels who have encountered extreme waves sometimes describe the experience more vividly. Without training, the sensation of a towering crest and sudden roll can feel overwhelming. Yet even in passenger narratives, the pattern of rapid succession appears. It is also notable that after extreme encounters, crews often report heightened vigilance for hours afterward. Even if wave heights return to predicted levels, the expectation of repetition lingers. The mind anticipates another cluster. Over decades, accumulated survivor accounts contributed to shifting scientific attitudes about rogue waves and grouped extremes. When instrument data finally confirmed what sailors had described, it validated generations of testimony. The silence after impact is therefore not only a pause in sound, it represents the gap between theory and lived experience. In that moment, statistics recede. Steel, wind and water have just interacted at near-limit conditions. When the ship continues forward and systems remain functional, the silence ends with relief. When damage is discovered, the silence transitions into focused action. These accounts ground abstract physics in human narrative. They show how interference, timing, structural limits, and psychology converge in real situations. And as we move from individual experiences to broader patterns, it becomes necessary to examine documented maritime disasters and near misses where extreme wave sequences played a role, tracing how rare alignments have shaped shipping safety practices over time. For centuries, sailors accepted that certain things at sea could not be forecast with precision. Storms could be anticipated by barometer drops and cloud formations, but the exact height of the next crest remained unknowable. Even today, with satellites scanning the oceans and supercomputers modelling atmospheric systems, there remains a boundary between prediction and probability. The question is not whether we can forecast storms. We can, with considerable accuracy over several days. The question is whether we can forecast the specific moment when 3 extreme waves will align in succession at a precise location. To answer that, we must separate large-scale predictability from small-scale determinism. Modern weather models simulate atmospheric motion using equations that describe fluid flow, thermodynamics, and energy transfer. These models ingest enormous amounts of data from satellites, aircraft, buoys, and ground stations. They calculate how pressure systems will evolve and how wind fields will shift. From these wind forecasts, wave models compute expected significant wave heights and spectral distributions. At this scale, prediction works well. Meteorological agencies can warn that a region of the North Atlantic will experience wave heights exceeding 10 or 15 meters. Ships can reroute to avoid the worst areas. Ports can close in anticipation of heavy swell. But within that predicted field of high waves lies complexity. Wave models typically predict statistical parameters, significant wave height, peak period, mean direction. They also estimate spectral shape, which describes how energy is distributed across frequencies. From these parameters, probabilities of extreme individual waves can be derived. However, the models do not track the exact phase of every wave component across the ocean. The ocean surface contains billions of interacting wave elements. Tracking their precise alignment in real time would require computational resolution far beyond current capabilities. Nonlinear amplification depends critically on phase relationships. A rogue wave or a Three Sisters sequence forms when many components align at a specific location and time. Slight changes in initial conditions can alter alignment outcome significantly. This sensitivity resembles what is sometimes called chaotic behaviour in nonlinear systems. That does not mean prediction is impossible at all scales. Short-term forecasting methods are emerging that attempt to identify developing wave groups in real time. Some research vessels and offshore platforms use wave radar to scan the sea surface ahead. By analysing the incoming wave field over distances of several kilometres, algorithms can estimate whether a large crest is likely to form within the next minute or two. These systems rely on measuring the current phase and amplitude distribution of waves approaching the vessel. If constructive interference appears to be building, a short warning may be issued. For smaller vessels or offshore platforms, even a minute of warning can allow partial preparation, such as adjusting heading slightly or securing loose equipment. However, this approach has limits. Detection range depends on radar capability. Reaction time depends on vessel maneuverability. A large container ship travelling at speed cannot alter course dramatically within seconds. Furthermore, not all amplified crests evolve predictably from measurable precursors. Statistical forecasting remains the primary tool. Instead of predicting the exact wave, forecasters estimate probability distributions. For example, in a given sea state, the probability of encountering a wave exceeding twice the significant wave height may be calculated. While the exact timing cannot be specified, the risk level can be communicated. This probabilistic approach guides engineering design as well. Ships are built to withstand conditions that statistically represent rare but plausible extremes. Safety factors incorporate uncertainty margins. Artificial intelligence and machine learning introduce new possibilities. By training models on vast data sets of wave measurements, researchers hope to identify patterns in spectral evolution that precede extreme amplification. These systems may detect subtle features in wave spectra that human analysis might overlook. Still, the ocean's scale and variability impose fundamental constraints. Unlike controlled laboratory conditions, the open sea is influenced by shifting winds, currents, and bathymetry. Measurement density is limited relative to total area. Even satellites cannot observe every square metre continuously. There is also the issue of data resolution. A satellite may pass over a region and record a significant wave height at one moment. Minutes later, conditions may have changed. Rogue waves and short clusters occur on timescales shorter than most global observation intervals. Predictability decreases as scale shrinks. At large scales, atmospheric systems follow patterns that can be modelled. At smaller scales, local interactions introduce sensitivity to initial conditions. The more precise the prediction required, the shorter the reliable forecast window. In practical terms, we can predict that certain regions during certain storms have elevated risk for extreme waves. We cannot predict that at 14:32 local time at a specific coordinate, 3 amplified crests will strike a particular vessel. Maritime operations reflect this reality. Ships avoid high-risk regions when possible. When avoidance is not feasible, crews prepare for the statistical possibility of extremes. Speed may be reduced, course adjusted to meet waves at safer angles, equipment secured preemptively. Forecast improvement continues steadily. Coupled atmosphere-ocean models now integrate current fields more accurately. High-resolution regional wave models capture finer spectral details. Data assimilation techniques incorporate real-time buoy and satellite measurements to refine forecasts continuously. Despite these advances, uncertainty remains inherent. Fluid dynamics at the ocean's surface involve countless interacting degrees of freedom. Capturing every variable with perfect accuracy is beyond current technological limits. There is a philosophical dimension to this boundary. The ocean is governed by physical laws, not randomness in the abstract sense. In principle, if every variable were known precisely, future wave evolution could be calculated. In practice, measurement precision and computational capacity are finite. Tiny uncertainties grow over time, altering phase alignment outcomes. This limitation does not represent failure. It reflects the nature of complex systems. Risk management therefore becomes central. Rather than eliminating unpredictability, maritime safety systems aim to reduce exposure. Improved hull design, better cargo securing standards, enhanced monitoring equipment, and more accurate storm routing all lower the probability that an extreme wave sequence will result in catastrophe. Predicting the unpredictable becomes a matter of narrowing uncertainty windows. Short-term detection systems may provide seconds or minutes of warning. Medium-term forecasts identify dangerous storm regions days in advance. Long-term statistical analysis informs design standards. Each layer reduces vulnerability but does not remove it entirely. The ocean retains the capacity to produce rare alignments that exceed expectation. That reality demands humility in engineering and vigilance in navigation. And as we look ahead, emerging technologies and evolving climate patterns raise new questions about how frequency and intensity of extreme wave events may shift, guiding us toward examining what the future may hold for ships crossing increasingly dynamic seas. There is a quiet assumption built into modern engineering. If something can be measured, it can be managed. If it can be modelled, it can be controlled. Ships are routed by satellite, guided by GPS, stabilised by computer systems, reinforced by advanced materials. Weather forecasts extend days into the future. Steel grades are tested under extreme stress. On paper, the ocean has become a calculated environment, and yet the three sisters remain possible. They are not evidence of chaos beyond physics. They are evidence of limits of prediction, limits of structural tolerance, limits of human control over systems that operate across vast scales. When three amplified waves rise in succession, they reveal something fundamental about control. We can reduce risk, we can design for probability, we can observe and respond, but we cannot command alignment of energy in a nonlinear fluid system spanning thousands of kilometers. The first lesson is scale. The ocean is not simply large, it is dynamically immense. Wind systems extend across continents, currents flow across basins, wave energy travels for days after storms dissipate. A ship, no matter how massive, is small relative to these processes. Control over a vessel does not translate to control over the environment it moves through. The second lesson is timing. Control works best in steady systems. When inputs are predictable, responses can be optimized. But the three sisters arise from brief alignment. They depend on phase relationships that shift within seconds. Even if a captain recognizes rising danger, the time window for meaningful adjustment may be too narrow. The third lesson is design humility. Engineers design within statistical frameworks. Safety factors are chosen carefully to balance strength and efficiency. Absolute invulnerability would require impractical overbuilding. The three sisters remind designers that rare events exist beyond average assumptions. They inform incremental improvements in hull reinforcement, monitoring systems, and operational protocols. The fourth lesson is adaptability. Control does not mean domination, it means adjustment. Ships that survive extreme wave encounters do so not because they eliminate wave force, but because they adapt to it. Heading changes, speed reductions, ballast adjustments, cargo securing, all are forms of responsive control rather than absolute command. There is also a psychological lesson. Humans prefer narratives of mastery. We map coastlines, we calculate trajectories, we chart shipping lanes across every ocean. The existence of rare, amplified wave sequences challenges that narrative. It reminds mariners that respect for environment remains essential. Respect is not fear, it is awareness of limits. The three sisters do not appear constantly. They are rare, but rarity does not equal irrelevance. Low probability, high impact events shape safety culture more profoundly than routine operations. Every documented encounter influences training, design standards, and forecasting improvements. There is a subtle shift in perspective that occurs when acknowledging these phenomena. Instead of asking how to eliminate risk entirely, Maritime practice asks how to operate safely within an inherently variable system. Modern vessels incorporate redundancy. Multiple watertight compartments limit flooding spread. Backup power systems maintain navigation. Reinforced bridge windows withstand higher impact loads than in previous generations. Hull stress monitoring systems provide real-time feedback. These measures do not prevent waves from forming. They reduce consequence. Control in this context becomes layered mitigation. Weather routing software analyzes storm trajectories and suggests safer paths. Captains choose routes that avoid peak conditions when possible. If avoidance is not feasible, preparation intensifies. Crew briefings emphasize heavy weather procedures. Equipment is secured early rather than reactively. There is also the lesson of continuous improvement. For decades, rogue waves were considered myths. Once measurement confirmed them, engineering standards adjusted. Window strength requirements increased. Design wave load assumptions were revised. Research into nonlinear wave modelling accelerated. The Three Sisters pattern reinforces that observation precedes theory. Sailors noticed sequences before equations described them. Listening to lived experience improved scientific understanding. Control improved not by dismissing anecdote, but by investigating it. Another lesson lies in probability perception. Humans tend to underestimate rare risks in the absence of recent experience. If a crew sails for years without encountering extreme clustered waves, complacency can grow. Safety culture counters this by training for unlikely scenarios regularly. Drills prepare crews for events they may never personally experience. Control, therefore, includes memory. Institutional memory of past incidents informs present caution. There is also a broader reflection. In complex systems, oceans, climate, financial markets, ecosystems, rare events emerge from ordinary processes interacting in uncommon ways. The Three Sisters are not anomalies detached from physics. They are products of the same wind, gravity, and current that generate everyday waves. What changes is alignment. Recognizing this reframes control as probabilistic rather than absolute. We influence exposure, we strengthen resilience, we improve detection. But we accept that total certainty is unattainable. That acceptance does not diminish technological achievement. It clarifies its boundaries. For a vessel crossing the Southern Ocean in winter, control means choosing the least severe path through forecasted storm fields. It means monitoring wave spectra. It means preparing for the possibility that, within predicted high seas, an amplified cluster may arise. For engineers, control means refining models to better capture nonlinear effects. It means adjusting design criteria as data accumulates. It means balancing economic efficiency with safety margin responsibly. For scientists, control means improving measurement density and resolution. Satellites, buoys, and shipborne sensors collectively reduce blind spots. And for mariners, control ultimately means readiness. The Three Sisters teach that control is dynamic. It is not static authority over the sea. It is ongoing negotiation with forces larger than any individual vessel. When three waves rise in succession and strike a hull built of steel, what survives is not dominance but preparation, adaptation, and resilience. And as global shipping continues to expand, and as climate patterns evolve, the question becomes not whether we can eliminate such rare phenomena, but how we continue to refine our relationship with an ocean that remains governed by rhythms deeper than any single human design. A ship at sea can feel stable. From a distance, a large vessel crossing open water appears steady, almost indifferent to the motion beneath it. The hull cuts forward. The wake trails behind in a straight white line. From the bridge, instruments glow steadily. Engine revolutions remain constant. On calmer days, the ocean surface rolls gently, and the illusion of stability becomes convincing. But stability at sea is never absolute. It is conditional. A vessel floats because buoyant force balances weight. It remains upright because its centre of gravity sits below its metacenter. It advances because propulsion overcomes drag. Every aspect of that stability depends on equilibrium between forces. Change the balance, and behaviour changes. The three sisters expose how thin that equilibrium can be. When three amplified waves rise in succession, the illusion of steady motion dissolves. The deck tilts sharply. The bow climbs beyond expected angle. Steel flexes audibly. In those moments, stability reveals itself as negotiation, not permanence. The sea itself embodies constant motion. Even when the surface appears calm, energy moves invisibly beneath. Swells generated thousands of kilometres away pass under hulls without drawing attention. Currents flow silently below. Tides shift entire coastlines over hours. What looks still is rarely still. Humans, however, seek solid ground, physically and psychologically. We build structures that resist motion. We prefer floors that do not tilt. We define safety as the absence of unpredictable change. When we board a large ship, we carry that expectation with us. Modern engineering strengthens the illusion. Steel hulls, stabilizers, weather forecasts, digital charts. These tools reduce variability and experience. They create conditions where the ocean feels manageable. But the ocean does not become static because we improve our tools. The three sisters are reminders that beneath steady averages lie fluctuations. Most of the time, those fluctuations remain within manageable limits. Occasionally, alignment pushes them beyond expectation. This tension between perceived stability and underlying motion extends beyond ships. Consider how a vessel at anchor appears fixed in place, yet currents pull gently, wind shifts subtly. The anchor chain adjusts constantly, even if motion is barely visible. Stability exists because adjustments occur continuously. Likewise, a ship underway does not resist waves by being rigid. It flexes, it rises and falls, it absorbs energy. Its stability is dynamic. Remove flexibility, and stress would concentrate until fracture occurred. The self operates in similar ways. A crew member standing watch during a storm maintains composure not because fear is absent, but because training, experience, and focus modulate reaction. Emotional equilibrium is maintained through small adjustments, breathing, communication, procedure. When three extreme waves strike in succession, both ship and self undergo rapid recalibration. Steel bends slightly and returns, muscles tense and release, instruments are checked, systems are confirmed, stability reasserts itself through adaptation. The illusion lies in believing that stability means immobility. In reality, stability at sea is continuous compensation. The ocean's surface never freezes in place. Even in apparent calm, microwaves ripple. Wind strokes the surface lightly. Currents shift temperature layers below. A flat horizon can transform within hours if pressure gradients tighten. The same applies to climate patterns. Storm tracks vary seasonally. Ocean temperatures fluctuate annually. Long-term changes alter baseline conditions gradually. Stability across decades is relative, not fixed. When mariners speak of good weather, they mean conditions within acceptable limits. They do not mean absence of motion. The ship still rises and falls gently. The deck still shifts beneath feet. The crew adjusts unconsciously to that rhythm. Extreme wave clusters disrupt that comfort. They compress motion into sharp intervals. They expose the dynamic nature of equilibrium. There is also a philosophical dimension to this exposure. A giant ship crossing an ocean can feel like proof of human mastery. Routes plotted precisely. Cargo delivered across continents. Communication maintained via satellite. The scale of coordination required to operate global shipping networks reinforces confidence in control. Yet a brief alignment of wind, current, and phase can test that confidence. The sea does not act with intention. It follows gradients of pressure and gravity. But in doing so, it reveals that large systems contain variability at every level. The illusion of stability arises when variability remains within expected bounds. We internalize those bounds as normal. Rare deviations feel disruptive, not because they are unnatural, but because they exceed our habitual range. From a design perspective, acknowledging this illusion leads to resilience. Instead of designing for static perfection, engineers design for movement. Instead of assuming constant calm, navigators prepare for change. There is a quiet humility embedded in maritime culture. Respect for the sea persists even among those who cross it routinely. That respect is not superstition. It is recognition that equilibrium depends on forces larger than any single vessel. After surviving a Three Sisters encounter, crews often report a renewed awareness of motion. Even moderate waves feel different for a time. The horizon's rise and fall becomes more noticeable. Then gradually, routine resumes. The illusion rebuilds. But somewhere in memory remains the knowledge that stability is conditional. The ocean teaches that balance is achieved through constant response. Steel must flex. Hulls must distribute stress. Crews must adapt. Forecasts must update. Observation must continue. The sea in its vastness does not promise permanence. It offers patterns, probabilities, rhythms. Within those rhythms, ships move, people work, cargo crosses continents. The Three Sisters are not contradictions of order. They are expressions of it, rare alignments within a system governed by law yet shaped by complexity. And perhaps that is the final lesson. Stability is not the absence of motion. It is the capacity to endure motion without breaking. The sea continues to move. Ships continue to sail. The balance between them is never fixed, only maintained, moment by moment, crest by crest.